it. Yeah. And then we can get
Okay. All right. So we can start.
Yeah. Okay.
So it's recording.
It should say recordings started. It should say the recording. No, you're recording, but
Okay.
why don't we have no sounds? I don't know. That you're recording.
Yeah.
Usually it says something, but.
Right. Should be okay.
Yeah. Okay. No idea why we don't hear this.
Shoot, I want to go back.
Yeah.
Okay.
So good morning, everyone, and thank you for being here. So today we'll have a training given by Professor Tobias Fischer from now University of California, Santa Barbara, and he's going to talk to us about volcanic gas. So Tobias, the floor is yours.
Perfect.
And thank you for everyone joining online.
Sure. Thank you very much, Catherine, again, for hosting me and making this project happen and the opportunity to talk about research and some results. So what I thought I would do today is give you an overview of some applications and interpretations of volcanic gases, but also hydrothermal and tectonic volatiles. I have a lot of material, and we can use as much of that as we want as we go forward. And you can always ask me questions if you have any as I move along. For the people in Zoom land, if you I have a hard time monitoring the chat and stuff like that. So maybe save your questions till the end, and then type them in the chat, and I can look at the chat after, and then we can address your questions as well. So, okay, so if we just hang on, how do I advance? There, okay. So, when we look at the Earth, of course, we are very familiar with this. If you're an Earth scientist, you know very well that we have the mantle and the asthenosphere, and we have the lithosphere, and we have the continental crust, and we have subduction of oceanic lithosphere and oceanic crust into the mantle, and that process causes dehydration of the plate, and water comes off the slab. Water and other volatiles come off the slab. Those volatiles enter the mantle wedge and cause the mantle peridotite to melt because it lowers the melting point of the mantle peridotite as you add water to it. Now, that causes arc volcanism, and this is very well known. This general process is very well known. In the continental setting, there are some other processes. In general, also, we have upwelling of maybe plume material or mantle material that causes or is related to the rifting process, the extension process in continental settings. So this just gives you a very broad overview of the tectonic situation on Earth. Now, what I'm going to talk about, of course, is that volatiles are important in all of these settings, okay? And volatiles are emitted along the mid-Atlantic or mid-ocean ridges and along arcs, volcanic arcs, and as well as along the continental settings, continental rift settings. The composition of these volatiles are very different depending on where you are going in terms of the tectonic setting. In volcanic settings along the arc, we have all of these volatiles: water, CO2, sulfur, nitrogen, and so on. In continental rift setting, the emissions are generally CO2 dominated. And that doesn't mean that the mantle does not release water and sulfur. It just means that these other more reactive volatiles might be caught up in a hydrothermal system or react with materials in the continental crust and don't make it to the surface, okay? So we have to always consider processes that happen close to the surface and processes that tell us about the source of the volatiles in order to understand the whole picture. right? And that's kind of what I'm going to talk about. So the first part of this presentation is to show you what we think we know about really the magmatic component, right? What comes from the magma. And this is a picture of a recent eruption in Iceland, 2023 eruption in Iceland. And you see clearly that this gas comes from the magma. There's no doubt that this magma here is at the surface and it's degassing its volatiles directly to the atmosphere. This magma has a temperature of about 1,200 degrees C. It's been measured using devices that, infrared devices that allow you to determine the temperature. And so also petrologic methods allow you to determine the temperature of that magma. And clearly, this gas is directly coming from the magma. So when volcanoes erupt, they produce like the Iceland eruption, very spectacular images, very spectacular pictures. And during those eruptions, gases as well as volcanic material are emitted into the atmosphere. And here, this is Sarychev Peak eruption, quite some time ago. And you see gases and volatiles and ash going up. Also, you see pyroclastic flows coming down on the side of the volcano in all of these directions, right? So clearly, those eruptions pose a lot of hazards. However, when we look at the emissions of eruptive volcanic SO2, we can determine those emissions now very, very easily using satellites, right? So the TOMS satellite, the TOMS Total Ozone Mapping Spectrometer is a satellite that was launched in the late 70s. And in fact, it was launched to map the ozone hole. You may have heard of it. A side effect of the TOMS is that it also can measure sulfur dioxide, right? So when Chichon erupted in 1982, people saw a big signal on the TOMS. And they were wondering, why do we have this big ozone signal? And they asked volcanologists, was there any eruption or what was going on? Why do you think we see the signal? And yes, indeed, El Chichon erupted. And clearly, volcanoes do not emit any ozone. So it became clear that TOMS can also measure sulfur dioxide, right? And that's the story of volcanology, that we don't have any dedicated instrumentation to monitor anything, really, in terms of satellite instrumentation. There's no dedicated instrumentation to monitor volcanic sulfur dioxide. There's no dedicated instrumentation to monitor carbon dioxide from volcanoes. Everything, all the data that we have is kind of piggybacked on by smart people figuring out how to use satellites or other things, make them work for volcanic emissions or volcanic processes. So the TOMS continued on. It detected the Pinatubo eruption, detected the Nabro eruption. And so as long as the sulfur cloud goes high enough into the stratosphere, the TOMS can detect it. More recently, there are more sensitive instruments, OMI and OMPS instruments that are more sensitive than the TOMS. And they can, in fact, detect very low levels of sulfur dioxide, okay? But again, they were not made for volcanoes. They were made for other purposes. Like volcanologists like Simon Karn and others at NASA, they manipulate the data so you can see the sulfur dioxide emissions from volcanoes. That data is openly available. Anyone can download that data and you can make plots like that using the NASA website. Now, what's really important to understand, however, and especially for this environment where we are in, is that passive degassing is very, very important, right? What do I mean by passive degassing? Passive degassing, I mean any degassing without eruption, okay? So what you see here is a famous picture of Etna, again, from the International Space Station in Sicily, right? So down here, cut off here. But here's Etna, volcanic plume, without any eruption, right? So the magma is just continuously degassing and providing emissions to the atmosphere. Likewise, we have diffuse degassing, and we will talk about this probably this afternoon a little bit more. And those are emissions that are occurring without any volcanoes, right? So just emitting through the ground. Now, what you see here is that we can look at passive non-eruptive degassing, and this is just the number of days with detected SO2 degassing over a certain time period. And so that means that the TOMS just sees a cloud of SO2. And you see that Nyiragongo, near Margira, have very high numbers of days where we have sulfur dioxide degassing from the volcano. And Nyiragongo, near Margira, are really one of the most important volcanic degassers in the world, right? And have been at that level of degassing for a very long time. I'm going to talk about that a little bit more. So here you have Popocatépetl in Mexico, Kilauea, Hawaii, Brim in Vanuatu. The top 4 or 5, here's Bagana in Papua New Guinea, Tungurahua, for example, in Ecuador. So the top 4 or 5, they change positions a little bit, but in general, we have a group of maybe 10 volcanoes in the world that emit most of the gases. And we did a lot of work to quantify this, and it's not important to go into that right now. But if you want to know the total emissions of volcanoes, you can focus on these top emitters, right? On the other hand, there's many, many, many volcanoes in the world, and this is not the complete list, that emit gases through the atmosphere all the time. So importantly, the eruptive degassing in terms of total emissions to the atmosphere is only 10%. The passive degassing is 90%, right? So of the total emissions into the atmosphere, eruptions are only 10%, even though they're very spectacular. They contribute only 10% to the global budget of CO2, SO2, water, and so on, degassing to the atmosphere. And this becomes very important when you are trying to model the global volatile cycle. How do volatiles move from the interior to the Earth to the atmosphere? And it becomes incredibly important when you are working with climate scientists who try to produce climate models and understand the contribution of volcanic emissions into their climate models. So that is an important finding that has been made a long time ago, really by Andres and Kazlok, back in the late 90s, where they looked at Central American volcanoes and figured out that most of the passive degassing, most of the emissions are due to passive degassing. So it's been known for a long time and has been confirmed through several more recent studies. Right. So now let's talk about volcanic gases. Right. So we have volcanic, magmatic, and hydrothermal gases. And we can sample them from fumaroles, bubbling springs, volcanic plumes, geothermal wells, diffuse emissions. And then we have tectonic gases that are not related to volcanoes. And we can sample them again, maybe at fumaroles, right? If there are some vents that are not really volcanic, but you have sometimes these cold CO2 vents, for example, right? Mazucos, bubbling springs, diffuse emissions, geothermal wells, okay? So, volcanic versus tectonic. Volcanic processes have to do with eruptions, with magma degassing, with modeling of how magma degasses, how magma moves from the volcano, from the magma through the volcano to the atmosphere, how it degasses. Has to do with monitoring, prediction of volcanic eruptions, forecasting of the type of volcanic activity. So that's really applications to these aspects. whereas tectonic gases are more related to understanding global volatile budgets, the sources of gases, meteoric water versus magmatic water, and combining geophysical techniques, for example, with geochemical techniques to understand some of the processes that happen at depth. This is a picture that I always like to show because it really encapsulates quite well what we're talking about. And Giovanni Chiodini and I wrote this chapter in Encyclopedia of Volcanoes now 10 years ago. It's a chapter that's, I think, quite general, right? It gives you a very broad overview of volcanic, magmatic, and hydrothermal gases and some of the applications. And Giovanni made this diagram, or somebody made it, and he contributed it to this chapter. It's very simplified, right? But essentially you have the magma down here. What does that magma look like? We can talk about this later. But it's the source of all these volatiles, okay? And this magma can sit maybe at 5 kilometers depth, right? That's just kind of like a common depth of where we often see magma bodies under the volcano, right? Of course, there's magmatic systems deeper down, and we'll talk about that a little bit later. But for this, at this point, the magma has all these gases dissolved in it, right? And then, just like with the lake, as the solubility is exceeded, bubbles form, and these gases are emitted to the crater, right, through crater fumaroles. So here, you would get very high temperature gas emissions, right? You would get temperatures that are, could be magmatic even. And the composition of those fumaroles will be very much CO2, H2S, SO2, HCl, HF, these kinds of gas compositions. Now, what's important though is that we always have water, or very often some water, in the edifice of the volcano. Hydrothermal water or meteoric water that gets heated by the magmatic input, by the gases, by the heat. And so these gases react with the water. And those reactions can be seen to occur if you sample thermal springs on the flanks of the volcano. So if you sample the water and you look at the composition of that water, you can clearly see a magmatic input, right? You can clearly look at the gases that are coming out of those springs and make a connection to the magma most of the time, right? So, however, as this water travels further and further away from the volcano, it becomes more and more affected by processes happening in the crust that neutralizes that water and changes the composition of the water and the gases. So essentially, and we'll get back to that, if you're interested in looking for geothermal energy, you want to drill pretty close to the heat source. But if you tap into this area here, you're going to have a lot of acidity in the water, right? And it's going to be hard to deal with if you're trying to install a geothermal plant. So therefore, often geothermal plants are more in the outflow zones. Here, you have more neutral water, but you get still some of the heat. We'll talk about that in another part of the lecture. Now, what's very important to understand, and we talked about this yesterday extensively when we talked about the lake, is, and it's really fundamental, and it's great that Catherine is working on improving solubilities in water at higher pressures of CO2 and methane, relevant for Lake Kivu. So what's really important to understand, very fundamental work that was done, this is summarized in 1994 by Holloway and Blank, but the work on solubilities of water and CO2 involved in magmatic systems has shown us that the pressure is a very, very important factor in terms of dissolving water in magmas, okay? So what I'm showing here is the maximum solubilities of water in magma and CO2 in magma, right? You look at this diagram and say, okay, yeah, that makes perfect sense. But do you all know how to read such a diagram? You know what it means, right? So I'll just walk you through it, okay? So if you have, for example, a rhyolite melt, okay, at 850 degrees C, the rhyolite melt at 2 kilobars pressure, 3 kilobars is about 10 kilometers depth. You can dissolve about 5 weight percent water, okay? So that means at 2 kilobars pressure, which are about 7 kilometers down, so that's where the magma is, you can have about 5 weight percent water in the melt dissolved in it, okay? It makes no bubble, nothing. It's in there. It's like you drink your Virunga, sparkling water, and you look at the bottle, there's no gas in it, okay? So it's like that, right? The gas, the water is completely dissolved in the melt. And likewise, for CO2, at 2 kilobars pressure, please go back. No. Oh, I want to go back. Okay. So likewise, if you have 2 kilobars pressure, rhyolite, this line here, shows us that we can only dissolve about 0.1 weight percent CO2, okay? Now, clearly, you can dissolve a lot more water than CO2 in a magma at the same pressure composition and same pressures and magmatic compositions. That means that at the same conditions, the magma just can't hold as much CO2 as it can hold water, right? And the other thing, of course, is that if you go up in pressure, you can dissolve more, right? Now, conversely, if you are at 10 kilometers depth, okay, and you have the maximum dissolved in the melt, 7 weight percent, for example, in a rhyolite, and you lower that pressure to 1, so the magma rises up, but what's going to happen is the gas will exsolve from the melt, and it'll form bubbles, okay? And so this gas has to go somewhere, right? The water, the CO2 has to go somewhere, or gas is always going to go up, right? So it's always going to go up. It's going to find its way up to the surface, and it'll produce that passive degassing that we talked about. Basalt has slightly different solubilities, and this is an old diagram. There's maybe somewhat better data now, but in order to show you the principle, this is very, very useful. We have programs that when I was teaching here last year, we used melts, we used volatile calc to calculate exactly how much you can dissolve in a melt. Why is this important? Well, volcanic eruptions are driven by volatiles. If there is no volatile in the melt, you don't have the energy to produce an explosive eruption. And so knowing how much water, CO2, sulfur is dissolved in the melt is really important to assess what kind of volcanic eruption, what kind of volcanic activity you can potentially have, right? So if your magma is completely degassed, it essentially can't erupt, right? It'll erupt, but it'll just maybe make a little lava flow, nothing like explosive. Okay, so this is not the topic of this talk, but knowing that the water and CO2 contents of melt is very important to understand volcanic activity. So take home points from these two slides, from this slide, is that CO2 is much less soluble in melts than water, and both are really pressure dependent. Now, also, this is a diagram that shows us the water phase diagram, pressure versus temperature, and looking at these relevant. So this is down 3 kilometers. Okay, we see that if we are at these high temperatures and high pressures, we're really dealing with a supercritical fluid. So we can't really say it's a liquid or it's a gas. It's really a supercritical fluid in those conditions. So it has quite low density, okay? Has quite low density, even though we're at high pressures, right? Has low density, it's a vapor-like fluid at magmatic temperatures. Even if you go, below, above 1 kilometer depth or so, you're going to be in the supercritical region, and that has implications for how these fluids are going to move and potentially some of the chemical reactions that might be going on at those conditions. It's not something that we're going to talk about in detail in this lecture, but I just wanted to make you understand so you're clear about we're dealing with these high pressures and high temperatures, so we're in a supercritical environment. This is water, right? This is for water. And how do we go about collecting these samples? Now, what I said is the magma, as it releases its volatiles, these volatiles will go out to the surface. There's essentially two ways of causing the magma to release the volatiles. One, we just talked about, the pressure decreases, right? Magma moves up, solubility changes, gases come out. The other one is essentially if you crystallize the magma, okay? So we'll talk more about that, but magma is a mixture of melt, of crystals, of gas. And in fact, if you look at a magma chamber seismically, people will tell you that, well, maybe we have 10% melt, maybe we have 14% melt, 15%, maybe 20% melt. But usually we don't have much more melt than that. So most of the magma chamber is really solid. And as that solid, as that melt cools, or as the magma chamber cools, you will continue to crystallize. And so the amount of magma that's around is going to get smaller and smaller. And so the gas that's in that magma will have no place to go, is essentially exceeding the solubility in that little pocket of melt, and the gas will come out. Right? So that's what they call, or what we call second boiling, right? When you have essentially just crystallization of the melt and the gas is driven out due to that. So therefore, if you have a magma body sitting underground, just crystallizing over time, right, over decades, thousands of years, the gas will have to go out, right? Because the crystals don't hold the water. Olivine, if you crystallize olivine, if you crystallize pyroxenes, if you crystallize feldspars, they don't have a high water content. So they don't accommodate the water. And the water, therefore, will go out, will be released to the atmosphere. And that's, again, what makes up this passive degassing that I talked about. Are there any questions so far? Make sense? Yeah. What's your question? That's okay. Yeah. Good question. So the question is for those online, the free data that NASA produces, and what's the frequency of the data? It very much depends on the satellite, right? And the instrument on the satellite. So the TOMS instrument, I believe, produces one image of the entire Earth, almost every day, right? So some satellites, they have special paths, and it takes more time to collect the data. But the data frequency is very, very quick, very, very rapid, very often. It depends again on the satellite. But for example, we use TOMS data or OMI data essentially to get a picture of the entire Earth degassing in one time period, which we consider the same time period. So geologically speaking, it's collecting data very, very frequently. Okay? So, and you can find all that data if you go to the NASA websites, and they give you very good information about the frequency of the measurements. For some areas, the data is not as good. So the polar regions, for example, are more difficult for TOMS data to be acquired because TOMS relies on UV light. And so in the polar regions, half of the year you don't have sun or very little sun. So therefore, you don't get very good data for those volcanoes. So Iceland, the Aleutians, for example, Kuril Islands, often you don't get data in the winter or in the southern part. There's not that many volcanoes, but you wouldn't get a lot of good data in the austral summer. So yeah. Does that answer your question? Yeah.
As you know, they are neighbor volcanoes.
Yes.
Now, from those data from satellites, how can we know that those data are coming from Nigeria? Because Nigeria, it always places. How do we know?
Right. So you're talking about the resolution, the spatial resolution of the satellite images. And yeah, you're right. I don't know the details of the spatial resolutions of these satellites. But from what I understand is that the OMI satellites and the OMS satellites have very good spatial resolution. And you can really identify plumes from individual volcanoes. So for those kinds of satellites, you should be able to see whether it comes from near Margira or from Nyiragongo. With TOMS data, has a bigger footprint, and so for those measurements that are back in time, further back in time, it might be difficult to say if it's from Nyiragongo or not. So again, it depends on the footprint of the measurements that you make. But for example, I know that volcanic eruptions that are in remote areas in the Aleutians, for example, and the volcanoes are also closely spaced, not as close as Nyiragongo here, but you can identify very clearly what volcano it is that is emitting the gas. Now, of course, once the gas is emitted, then it disperses into the atmosphere and it moves around, and then it becomes more difficult. But if you see, for example, an eruption or a pulse of gas coming out, you can really identify the source quite well. Yeah.
Now, do you think that there is any impact or influence of this volatile, the presence of volatile in the dike opening? If so, how can we recognize the pressure due to the?
Yeah, we'll talk about that a little bit later. But I think what you're asking me is, would we see a signal if there's a dike opening in the gas composition or in the gas emission? Exactly.
I want to know if there's any force due to the presence of those gases.
Yes. Yes.
Opening the dike.
Yes. Yes, there is. Yeah. If you have enough gas pressure, it can maybe not open the dike, but it'll open the crust above the dike, if you just have enough gas pressure. It just depends on factors like depth and so on. Okay. And it depends on how much gas there is in the magma. Yes.
Elective. So always have to take into account methane.
Right.
So I would like to ask if other gases like sulfur have been kept with high pressures.
There is clearly sulfur in Lake Kivu gas. We can smell it. Very, very strong sulfur smell. And the previous work that was done more than about 20 years ago now, very, very nice work they did not analyze for the sulfur gases in those samples. So they also, for example, didn't analyze for helium, right? So we don't know how much sulfur and helium is in those gases, but if these gases originate from magma, you would expect that there is some sulfur and some helium, for example, in it. The samples we collected just last week, we will try to analyze for those components to perhaps get a more complete composition of the volatiles that are dissolved in those waters. Right, so yeah, we can see this is in northern Chile, and this is your typical volcanic magmatic gas, right? Here's the plume, and you can insert titanium tube into this fumarole, and then you have some bottles, and you can sample this gas, right? And that's from a gas workshop that happens every 3 years since the late 1980s, mid 1980s. People come together and we sample gas. Yeah, what's your question?
See where that is somebody.
Yeah. Yeah, so the danger is really the sulfur and the chlorine is very acidic. So, we have masks here, but for example, the wind is all blowing that way. So here, you're totally fine without mask. Like this lady, she doesn't have mask, this guy. Bruce Christensen, he's wearing mask. Right, so generally, yes, you want to wear a mask because the wind can change and then you're in the middle of the gas. Okay, so again, what's the composition? This picture in the back is actually from Erta Ale volcano in the ICTP-EAIFR region, where we sampled gas of 1,000 degrees, 1,030 degrees C. The composition here is not from Erta Ale. This is from another high temperature volcano. I'm just showing this to you as a typical example of a magmatic gas, okay? Now, what I want to point out is 95% of magmatic gas is water. And that's very consistent with what we talked about before, that you can dissolve a lot of water in melt, right? So once that melt degasses, of course, most of the gas is going to be water. And then it's followed by CO2, SO2, H2S, HCl, HF. And then you have these other kind of trace components, nitrogen, argon, helium, you have hydrogen. There should never be any oxygen in those temperatures. And you might have some methane and some CO. And you can get all the isotopes of these gases from those samples that you collect in these bottles. Right? So coming back to your question, if there is a magma underneath Lake Kivu, and that magma is similar to what you see at Nyiragongo, then the gas that comes off of that magma is going to be like that. All right? So, but at the surface, you're not going to see HCl. You're not going to see HF. Those gases will react with the rock or maybe with water, and you will not see them. They will get absorbed. They will get scrubbed out by processes happening at depth. But originally, the magma will produce this kind of gas. There's no question about it. Okay. So now this is just to give you kind of an overview and again to drive home the point that the three main components of volcanic gases are water, CO2, and what I've plotted here is total sulfur. So that is SO2 and H2S, right? And this is a Gegenbach style diagram. It's a little bit complicated to read, but essentially, if you have pure CO2, we would plot here. If you have pure water, plot here. If you have pure sulfur, we plot here. And for example, if you were to have no CO2 and you added water, we would move along this line. And what we do is we have these factors, 2 times sulfur, water divided by 50, in order to spread out the data points, right? Because 95% of the gas is water, and if you just plotted it in a regular way, all the little dots would be like over here in the water. And so we just kind of manipulate the way we plot it so to show the spread of the data. Now, arc volcanoes, so volcanoes that are related to subduction zones, tend to have this kind of water CO2 ratio. Okay, so there's a few outliers, but most of them have this water CO2 ratio between 25 and 150, and water sulfur ratios can vary quite dramatically, maybe from 1,000 to only 10 or so. Likewise, CO2 sulfur ratios, which I haven't plotted the ratios, but they vary quite significantly. Okay. Now, Ertaale sits here. This is in the ICTP-EAIFR region, not subduction related. And you see that it's different, but it's not that much different. Okay. It has higher CO2 than water, higher water, lower water CO2 ratio, significantly lower water CO2 ratio than arc volcanoes. But in terms of CO2 sulfur ratio is very similar to some of the gases from subduction zones. Okay, now let's talk a little bit about Nyiragongo again. And hang on, where am I going? Yeah, so let's go back into that. Right, so we talked about eruptive SO2 emissions. This is data from late 70s to 2015, 10 years ago now when Simon published this, but there are updated plots online. So you can go online to the NASA website, SO2 emissions website, and you will find updated plots that go up to, today, really. Now, eruptive degassing, passive degassing, we talked about a little bit. So Etna produces about 3 megatons of CO2 per year, and passive degassing or diffuse degassing is about 2 megatons in this region. We'll talk about this a little bit later. But again, you see the significance of degassing without any eruptions. And this is very important in the East African Rift. So let's talk about Nyiragongo Nyiramargira. Like Ben was saying here, I don't have to really introduce this volcano. You know where it is, you know what it does. But what you might not know is that all of these dots here, these are all from Nyiragongo Nyiramargira eruptions. All these where I have these arrows, all of these guys are from eruptions from Nyiragongo Nyiramargira. So that volcano is by far the most consistent high emitter of sulfur dioxide or carbon dioxide or water, which we can't measure, right? But we know it's emitted, of any volcano in the world, right? And so with each eruption, it produces about 1 megaton of sulfur dioxide, each eruption. And each eruption, and the eruptions happen every few years, as you know, right? Every few years, we have an eruption of these volcanoes producing these very high emissions. So Nyiragongo Nyiramargira are volcanoes that are very, very active, and they have a lot of gas in them, okay? Now, let's talk about this a little bit more. What does that mean? Where might this gas come from? We also have, we talk about Nyiragongo and Nyiramargira, but we can also talk about Oldonyilengai in Tanzania, which is a carbonatite, and it also has high emissions of CO2, however, not very well quantified to this day. But let's talk in detail about what does it mean, put it into perspective, this high emission of Nyiragongo. Okay, so CO2 emissions from Nyiragongo passive degassing is about 1,400 kilotons of CO2 per year. And that's published in a recent paper that we put together. Eruptive is about 700 kilotons of SO2 per year. And if we use a CO2 sulfur ratio of this, which is a common ratio, so we get 2,500 kilotons of CO2 per year. So I'm focusing on carbon dioxide here. It's a very, very important part of the system. So passive degassing is 1,400, eruptive degassing is 2,500 kilotons. So you see, Nyiragongo, Nyiramonjira, the eruptive degassing is in fact more than the passive degassing because it erupts so often, okay? So it's kind of an outlier because before we said most of the degassing is passive, not eruptive. At Nyiragongo, it's different. But we have a total of about 4 megatons of CO2 per year degassing. Every year, 4 megatons over more than 30 years. Right? So if you look at Kilauea, 1 megaton, Etna, 3 megatons, the entire mid-ocean ridge system is about 60 megatons of CO2. So it's a huge contributor of carbon dioxide to the atmosphere. And has been, for a long, long, long time. And ever since we've been making measurements for 30 years, but likely even before then, of course. Okay, now, does that mean there's a lot of carbon dioxide in the source of this volcano? Is it unusual to have such high CO2 content? So we can make a very simple calculation, and with more data, we can improve this calculation. But this is a very, very simple calculation that illustrates how we can think about CO2 contents of magmas. So if we have a flux of 4 megatons per year, right? We can accommodate that flux by increasing the magma flux or increasing the content of CO2 in the melt. Right? So if I have a very high CO2 content in the melt, and that melt degasses, producing that 4 megatons, I don't need a very high magma flux. So the amount of magma that degasses to produce the CO2 that I measure can be very small if the CO2 content of the melt is high. Likewise, if the CO2 content of the melt is low, I need a lot of magma to produce that flux, right? So it's just a mass balance calculation. Very simple. Everybody follow? Do you understand that? If you don't understand that, you have to tell me because it's important. So the more magma flux I have, the less CO2 I can have in the magma in order to produce what I measure at the surface. So I am assuming complete degassing. What is the magma flux of volcanoes? Well, it's very difficult to know that, but we have some data for Nyiramonjira. Now, there was an eruption. I think I've talked about this before in another talk, maybe. But there's a Nyiramonjira eruption that Albino et al. Measured, during this time, 0.3 cubic kilometers per year. Okay, and magma depth 12 kilometers. So if I just take that point, then take this magma flux, and I just plot it, on this line. Boom. Okay, so this is the magma flux from this one eruption. So that means that the CO2 content of that magma is 4,000 parts per million, more or less, right? So the magma, assuming that magma flux to produce this 4 megatons of CO2, I assume that this magma flux is constant and produces the emission of 4 megatons of CO2. That means I need about 4,000 parts per million of CO2 in the melt, completely degas to produce the emissions. So it's a very rough estimate of how much CO2 might be in the magma. If you have a lower magma or higher magma flux, the CO2 becomes lower. If you have a lower magma flux, the CO2 becomes higher. Okay, so, but let's go with this number, see what that means. Now, for Kilauea, they did a very similar calculation, a little bit more sophisticated modeling, but essentially Anderson in Poland did the same thing where they have the emission rate of CO2 from Kilauea, the magma flux rate, and the CO2 flux, and they measured essentially how much they extrapolated how much undegassed magmatic CO2 you have to have in the melt. Right. So here is, for example, the magma supply rate. You see, this is modeled 2 different times, 2001 to 2002 at Kilauea. And then this is in 2006. Magma supply rate increased. Okay. So it's a little bit more sophisticated than just my back of the envelope calculation for near Murajira. But you see here, near Murajira eruption, magma flux is quite high, 0.3. Okay. So it's higher than what Kilauea produced. Again, it shows us that this volcano, that is sitting like 10 kilometers from the Kivu, is very, very active. Right? There's a lot of magma moving through that system. Okay, so same thing. They use the magma supply rate and the flux that they measure at the surface. So at Kilauea, they get about 1% of this is use this time constant, this time constant. And you can read the paper, Anderson, Poland. It's a Nature Geoscience paper, 2017, very nice paper, where they go through the calculation. So again, you see that we have about 1% of undegassed magmatic CO2 concentration in the Kilauea magma that feeds these eruptions. That means that if you have 1% in the source, the magma saturates at about 30 to 40 kilometer depths. So think about that, okay? So 30 to 40 kilometers down from Kilauea, you're going to see bubbles of CO2 coming out of the melt, right? So the degassing is happening very deep because there is a lot of CO2 in the melt. Now, the near Murajira rough estimate plots about here. Okay? Of course, it's going to be lower because the magma supply rate is higher. Okay, makes sense? So how does that compare, right? So we can take the CO2 concentration of the magma to calculate the CO2 or the carbon concentration of the mantle that makes that. All right. So just if you're not familiar with this process, you have a solid rock, all right, and that solid rock melts, and that melt will have CO2 in it. Where does that CO2 come from? Well, it comes from the solid rock. So it's mantle CO2. And the more of that mantle you melt, the more melt you're going to make, and the lower the CO2 concentration of that melt is going to be at the same carbon concentration of the rock. Now, how much does melt? Well, good question. Again, we can use 10%, 10 plus minus 1%. And the carbon concentration use this melt fraction, and you use the molar conversion, you can get the mantle carbon concentration from that. And so that's essentially what I did here, mantle concentration of carbon, right? So we had the undegassed magmatic CO2 concentration, so that's in the melt. From there, we go to the mantle carbon concentration. And this here is for Kilauea mantle, right? About 2,250 parts per million of carbon in the mantle. Oldonyo-Lengai estimate that I did a long time ago was about 280 or less. We just provided a maximum, could be less. And then this is near Murajira estimate 100, but 100 parts per million. And then this is more mid-ocean ridge basalt, which is about 37 ppm, right? So anyway, there was some debate about what's more carbon content, but it could be 80, it could be 37. Right? So anyway, it's lower than Niramura-Jira melt composition or mantle carbon composition. Okay, so underneath Niaragongo-Niramura-Jira, we have, if this very rough calculation is more or less correct, we have a mantle carbon concentration of about 100 parts per million, which is not extremely high, okay? It's not super high. It's not as high as Kilauea. It's higher than more, perhaps a little bit. But you know, how good is that estimate? It could go back and forth a little bit. So if we were to improve that estimate, we would have to improve the magma supply number, I think. So why do we go through all this thing? Well, yeah, that's a question.
Now, why do you know those differences in the amount of carbon dioxide, mantle, and the Kilauea? And you have the mantle convection that you can homogenize.
Oh, yeah. Well, Kilauea obviously is a plume. Okay, it's a mantle plume. So that's why Hawaii exists as a type example of a mantle hotspot, a plume. And that plume is obviously, according to this, more rich in CO2. Whereas in the East African Rift under Niaragongo-Niaragongo, maybe you have some plume component, but it's possibly not as strong as under Kilauea. So what is the reason for those differences in CO2 content? Well, that's a good question. We don't know the answer to that. But the CO2 content of the mantle is not uniform. There are places that have higher CO2, some have lower CO2. So under mid-ocean ridges, there is a variation. You can read the paper of the Bouillet et al., very nice paper, where they have looked at glasses erupted along the mid-ocean ridges. And even there, they see variations from 5 parts per million to 327 parts per million. Okay, so these high numbers were questioned by Jones and Kurtz et al. In a later paper, but it's not a uniform contribution, not a uniform composition of carbon in the mantle. There are areas that are higher carbon, areas that are lower carbon, and clearly under Kilauea, under Hawaii, there seems to be a higher carbon concentration in the mantle than what we see in. So here is the work that was done at Kilauea. As I said, they did a very similar study where you have the magma supply here. You have a magma storage unit. They have the emission rate, right? They used 8,400 tons per day, emission rate plus minus this number. And then the model computes how much undegassed magma is coming up to supply those emissions. In Kilauea, it's a little bit more complicated. The magma actually moves down the East Drift Zone. So it moves down the East Drift Zone, and then it erupts here at the Pu'uo'o event, which, the eruption happened back in 2018, destroying a bunch of, a number of settlements and towns due to the magma flow. You see that at Kilauea, the magma can travel underneath the surface for quite a ways. I mean, it's tens of kilometers, really. But most of the CO2, in fact, degasses right here at Halemauma, the summit reservoir. Right? So the summit reservoir degasses most of its CO2, but the magma, the degassed magma, can move on further down. And here, most of the emissions are, in fact, sulfur dioxide. The sulfur dioxide is more soluble than CO2, so the magma will lose its CO2, but it'll hold on to some of its SO2. There's another reservoir here, and then the lava comes out. Now, if you think about this, there's some parallels to possibly Nyiragongo, right? Where you have the summit area degassing a lot, but the magma could potentially move in different directions, as we have seen the slides that Ben showed yesterday. So the approach that I showed for Nyiragongo Margira is exactly the same that these guys use for Kilauea. It's just that they have a much better constraint of magma supply. We don't have that constraint for Nyiragongo. Okay. So again, this magma will saturate at 30 kilometers depth. And just to again show you that Nyiragongo Margira is similar to Moore. It's not that much higher than Moore in terms of the mantle concentration. This I don't want to go into too much detail, but Levoyer 2017 wrote this very nice paper where they talk about, what happens when you have CO2 in the mantle, and how does that help with melting? Okay, there's a lot of parameters that are important, like oxygen fugacity and CO2 content. But for example, if you have a CO2 content of 37 ppm, a carbon content, right? 137 ppm CO2, 37 ppm carbon, it's just a conversion. You could potentially start melting make small amounts of melt at more than 250 kilometers depth. This is the melting curve. And this melting curve depends on different oxygen fugacities and so on. But you could potentially, that's the point, you could potentially start making tiny, tiny amounts of melt at very deep levels in this region here, 37 ppm carbon. If you have 5% carbon, okay, 20 ppm CO2 in the mantle, you wouldn't melt till you're pretty shallow, 70 kilometers. You're still pretty deep, right? But the point of this diagram is just to show you that we have significant impact of the amount of CO2 to produce melts at deep levels. This paper talks about this in great detail. So, near Margira, Kilauea, if you take this approach, the melting could potentially happen very, very deep because we have 100 ppm, 250 ppm carbon in the source. And so melting can happen very, very deep. And seismic images, this is from another part of the East African Rift. Mantle tomography shows areas of higher temperatures, perhaps little pockets of melt at very, very deep levels. So it is possible that melting happens at those deep levels, and that means that CO2 will go into the melt, and then if that melt moves up, the CO2 will eventually degas. So the source of the CO2 that you see at the surface, even maybe in Lake Kivu, could come from very, very deep. That's the point. If it's magmatic. How are we doing? Okay, we're doing good. Do we take a break or something? Or do we just crank through it?
We can take a break.
Take a short break? Sure, let's take a short break. Yeah. Are there any questions from the Zoom audience? I don't see anything in the chat. Yeah, if you have any questions, we're going to take a short break here. Going to have some coffee. So if you're in Zoom, you can get some coffee. Depending on where you are in the world, I mean, maybe it's
Go to your kitchen.
Go to your kitchen and get some coffee.
gas.
All right. We'll start again. Again, if you're online, if you have any questions, type them in the chat. See them later. Okay, we're gonna start again, guys. So how, when we think about melting occurring very, very deep, we should think about the fact that melt can be deep and that it can occur underneath places that are not necessarily right under the volcano. Okay. And so if we only monitor the volcano, we may miss a lot of information that might be happening in places where melting also occurs. And so we should, of course, focus our monitoring on volcanoes, but we need to be aware that melting can occur below areas that are not directly underneath a volcanic region. And that's shown here in the Kenya Rift Zone. Now, here's a volcanic area. Here's no volcanic area, yet you can have still some melting at depth underneath these areas. And if you have melting, you're going to release gases, and those gases can travel to the surface.
I think it's a crater in the middle.
Yeah, it's a craton.
Yeah.
So that's the Magyara. So the craton would be over here. And magmatic systems are not really a big blob of magma like I've shown before, but now what scientists are thinking is that it's really more like an area in the lower crust, in the upper crust, that is penetrated by magmatic sills and magmatic dikes that connect these different magmatic sill areas. And we can increasingly see these kinds of features with better and better seismic imaging. Now, what reactivates these magmatic systems is a question. And I don't have time to go into that, but research shows that some of these magma bodies, they hang out for a long time. Like, they can sit there for thousands of years, cool, crystallize, and then they can become reactivated. That's what we call cold storage of magmatic systems. They cool down, are stored underground, and then if there's an injection of new magma from depths or volatiles from depths, these magmatic systems can be reactivated, and then magma could migrate up into shallower reservoirs and then eventually erupt to the surface. So the point is that it's not just one big blob of magma, but we have different layers of magmatic lenses distributed throughout the crust. So essentially, we need to think about it in that way. And some of the gases could come from really, really deep. Maybe the CO2 comes from really, really deep down here. If there's some crystallization of this magma, second boiling, the CO2 could migrate all the way up to the surface and perhaps mix with other gases that come from shallower levels, perhaps water or sulfur dioxide that have a higher solubility in melts. Essentially, what you measure at the surface is going to be a complex mixture of gases being released from different levels. Now, of course, we saw this kind of slide yesterday, and we have Rongo right here, right? That's where we can measure the sulfur dioxide emissions using satellites and other techniques. And we have all these faults, right? Large fractures, fissures that are extending from the volcano all the way to the lake and also into the other direction and this direction here. And here's Kabuno Bay that you're probably familiar with, that had very high CO2 concentrations during the recent eruptive activity in the water. Right, so the volcano and the lake are very, very close and they are related tectonically and geologically. Are there faults under the lake? Yeah, most likely there are. Why would the faults stop here? Not going to stop here just because there's water. So I'm sure there's fractures and faults underneath the lake, extending probably the entire length of the lake because we're in the rift situation. And if you look here, of course, you have all this faulting. Here's the craton. The rift bifurcates around the craton, and it's expected to have large faults underneath the lake. Of course, those faults are covered by sediment, and we can't easily see them. We don't have a way to go down there and look at them like we have on land. We can map them, but certainly faults are underneath the lake, and that's most likely where the gases are coming up. Gas will always find the easiest way up. So here's the volcano. This is from the web. We never had such a nice shot, but volcano is very close to the lake, as you know. And the magma, is degassing. It is producing gas coming out at the volcano, but then that gas will interact with water. And you can just imagine the same situation where you have not just hydrothermal or meteoric water from rain, but you can have a lake, and that lake will absorb some of the gases that are coming from the magma. Now, again, magmatic systems, and I'm just showing you this diagram, which is a very nice summary from Edmonds and Woods 2018, where we have gas-rich eruptions, persistent degassing from the volcano. But underneath, we can have this larger magmatic system. Right? So here would be Nyiragongo, Lake Kivu could be over here. Right? Could be over here. So you can get a magmatic system that extends underneath the lake. You can get exhaust volatile rich melts at the surface. You can have accumulation of exhaust bubbles. You can have areas in the crystal-rich magma area, areas within the crystal-rich magma that have cracks and fractures, and volatiles will move through those. At the bottom of the magma system, this larger magma body might have injection of new magmatic volatiles and new magmatic melts, underplating. That can also cause overturn, buoyant forces, buoyant plumes, enclaves, and you get a mixture of deep volatile poor magmas and shallow volatile rich second boiling magmas closer to the surface. So it's a very, very complex system. It's not just a magma body with melt and some gas and some crystals. There are different areas in the magma body that will produce these features. And in every different place, you might get slightly different volatile compositions as well. So it's complex. It's complex. And ideally, we want to image this geophysically. And there's a nice study that I was a little bit involved in, but it was really driven by Brandon Schmand, where they did a very high density deployment of seismographs nodes in Yellowstone. So for those who are not familiar, Yellowstone is a large caldera system in the western United States. It's located right here. So that's the United States. Here's Wyoming. Yellowstone is sitting right there at the border between Wyoming and Idaho and Montana. So anyway, it's a large caldera system, and it has been monitored very, very extensively. However, what Brandon Schmand and his group did was they deployed many, many hydrophones in a cross section across Yellowstone and specifically across the mud volcano area, which is known to be an area where there's a lot of gas coming out, a lot of CO2 coming out. Mantle-derived volatiles are being emitted there. And they drove a truck, a vibro-sized truck, along this road, and so it's an active source study, and they were able to identify very detailed features underneath the caldera. And what is most striking, and I encourage you to read the paper, just came out earlier this year, they were able to identify this very sharp reflector here. Very, very sharp reflector that is at about 2 to 4 kilometers depth and extends over quite large distance, about 25 kilometers or so. And this reflector is across the mud volcano area. MV is here, that's mud volcano. And that mud volcano area has a very, very helium-3-4 ratio, which we will talk about later, 15 Ra. And this is where you have the biggest signal of a deep mantle degassing. So what does this reflector mean? And this, again, is not my expertise. I'm just summarizing, showing you what's written in the paper. But essentially, what they did in the paper was model that density contrast. And their best estimate is that you have a 50% water and 50% melt area in that region to explain that PCS-PCP ratio. So in order to get that, the best fit for the model is 10 to 15 volume percent porosity filled with bubbles and melt. Right? So the idea is that this layer is a layer that's rich in bubbles and melts. Right? So you have this part here, which is a silicate melt that has volatiles dissolved in it. So most of the magmatic system is like that. And then up here on top, you have this cap, thin cap that has exsolved volatiles in it. And it's about only 100 meters thick, but you have supercritical fluids, supercritical fluid bubbles in that layer here. So all the volatiles essentially are accumulating at this top of the magma chamber. Bubbles and melt mixed together, maybe 50% of each. So that's quite shallow, only about 4 kilometers depth, and it's been clearly imaged with those techniques. So it gives us a very good sense of how these magmatic systems look like, where the bubbles would be, how much bubbles there are, and where the melt would be. So, of course, this study requires that you put a bunch of hydrophones or nodes, sorry, seismic nodes, very densely distributed, and that you are able to drive a truck to make seismic waves in that same area. It is not realistic for Nyiragongo and Lake Kivu, but something like that would be really interesting to do, to get a better idea of where the bubbles are, where the magma is, what the melt distribution is, how the spatial distribution is underneath the lake. So techniques are out there to do this geophysically, and you know more about this than me. But this study is something that you might want to look at to see what could be possible. So, and then the modeling shows you what it could actually be. So again, let's see, we break for lunch, right? Noon?
Yes.
Okay, so just again to drive home the point that we have these different solubilities. These gas bubbles that were detected at Yellowstone, those are mostly CO2. Okay. Now, I'm going to skip over that. That's a lot of detail, how water actually dissolves in the melt. We don't need to go into that too much, but it dissolves as molecules, H2O molecules and OH. Very, very early work has shown that, again, water as it interacts with the melt, it will dissolve in the melt and break up the melt structure. And so it actually breaks up the melt structure, and that causes the viscosity of the melt to decrease. So the more water you have in the melt, lower the viscosity of the melt, which again has some influence on volcanic processes, right? So how we talked about how we can get volatile information from magmatic systems. We can collect these gases, and we can tell something about the composition. However, there's another way of doing this, and you can look at the rocks themselves, right? And that's a technique that's very often used and very powerful to get information about magmatic volatile compositions. So essentially what you do is you collect ash. This is a cinder cone, but it could be any cinder cone. And you collect some of the ash from that volcano. And then you essentially, this would be an eruption, could be Niragongo as well. You walk around Lake Kivu, you see all these little, you see cinders everywhere, right? So eruptions like that produce these cinder cones, produce this kind of ash. And within the ash, of course, you have crystals. Because remember, melt is crystals, magma, and gas mixed together. When that stuff erupts, like this, the magma quenches to glass, and the crystals are already there. So the crystals are formed in the magma chamber and blown out by the eruption. So the ash is actually a mixture of those three things. The gas will go out, but what you're left with are possibly some crystals, and those crystals are not perfect. They have little inclusions that are quenched glass, okay, or quenched to glass. So when the crystal forms, there are little imperfections and little bubbles of melt are trapped in the crystal. And when the volcano erupts, those bubbles or those little pockets of melt that are inside of the crystal will quench to a glass, right? So they will not crystallize, they will just be quenched. And you can then analyze that glass for its chemical composition as well as for its volatiles. Okay, so looks like this. This one here is a nice example. You see, this here is the melt inclusion, so that's glass. And then inside of it, you actually have a little bit of a crystal here. So this crystal crystallized, most likely from the glass, so maybe the glass wasn't cooled fast enough. Then you also have a little vapor bubble as well. That's a complication with melt inclusions. Melt inclusions are not perfect. Sometimes there's vapor bubble that forms inside of the glass. But when you do the analyses, you have to take account to all of these things. Makes it a little bit complicated. And there's a whole huge amount of literature on how to do this and how to make the corrections and so on and so forth. So I'm just going to show you what can be done with this kind of work. So when you have your crystal, the melt inclusion is entrapped here. It'll cool. It can form a vapor bubble. There can be exchange between the melt and the crystal and the surrounding magma body, right? Then the volcano erupts. You can enlarge these vapor bubbles and form some cracks. And you can also form additional crystals if the cooling isn't fast enough. So it's complicated, right? I just want to show the complexity of this kind of work. However, the data you can get from these types of crystals is very important because it tells you the water content and the CO2 content of the melts, right? So for example, here, this is an early paper 20 years ago, summary by Paul Wallace, where we see Cerro Negro volcano in Nicaragua. It has very high water contents. Okay, it's 6 to 8% water. It has 1,000 parts per million of CO2. Okay, so for example, here you have Stromboli, has 2 to 8% water. Oh, sorry, this is Stromboli here, a volcano in Italy, 2.5 to 8% water, 2,000 ppm CO2. Here's a normal morb, has very low water contents, 1,500 ppm CO2. So you can see that different volcanoes have different water contents and different CO2 contents. So that gets back to one of the questions we had, why is there more CO2 here, or why is there less CO2 in the mantle here, and so on. So likewise, we can have different water contents in different volcanoes. What we know now, and that's been known now for a long time, is that the CO2 content in these melt inclusions is all degassed, right? So the original CO2 content, like for Nira Murira, that I showed you based on that calculation, was 4,000 ppm. Okay, so it was here, right? And based on global CO2 fluxes and so on, the CO2 concentration in these magmas should be at least 3,000 ppm. And this is a very rough estimate, right? But the point is that these magmas, as you analyze the melt inclusions, have already lost their CO2. Most of it has already been lost due to passive degassing. So it's not trapped in the melt inclusion. Again, that drives home the point that I made earlier, that you can have degassing very, very deep, right? We said, oh, Kilauea degasses at 30 kilometers depth, Nyiragongo, Nyiragongo, perhaps even deeper, right? So that CO2 has already left the melt before it is trapped in those crystals. So even if you crystallize olivine, crystallizes very deep, the CO2 has already been gone, has already been emitted to the surface. It's not captured by this process. Water degasses much shallower, and so the water contents are probably more representative of the original water contents of the melt. Again, in terms of our situation here with Nyiragongo, Lekivu, and so on, the CO2 is likely coming from very deep, okay, and has been degassing through the magmatic system on its way up. So if you were to get a melt inclusion from Nyiragongo and you analyze its CO2 content, the number will tell you probably a minimum amount, but it won't tell you the maximum amount initially dissolved in the melt. Again, that's what we talked about earlier on, right? In order to get the original CO2 content of the melt, you have to do something like this, where you use the gas emissions and the melt production rate, then you can get an estimate like that. There are very few melt inclusion data for the East African Rift, very few data. And I worked with Mary Jo Brown on some rocks from the far region. The northern part, Arta Ale is here, and some other volcanoes, Gulf of Aden rocks that she has. Very, very detailed paper about volatiles in that part of the rift. But what I wanted to show you is just these plots here. You see that water contents are pretty high. This is Erta Ale, that volcano up here, high temperature gases that I sampled there a while ago. So those melt inclusions have very high water contents, 2 to 8%, and pretty high CO2 contents, 3,500. Okay. So even if those, so 3,500 is quite high, and we can imagine that these are even degassed, right? So the original CO2 content could be even higher, but we don't know how high because there's just no way of getting that information from the melt inclusions, okay? Likewise, sulfur contents are quite high, 2,500. I haven't talked about sulfur yet, and I won't talk about it very much. But again, we have high sulfur contents, we have high water contents for these melt inclusions in the northern part of the rift. We don't have much data in this part of the rift. We don't have much data in this part of the rift. So there's a lot of work that could be done on this. However, these analyses are challenging, and there's a lot of corrections and interpretations that need to be done. But it's very, very important to perhaps do this at some point. Katie Kelly and I wrote a summary chapter for Trees of Geochemistry, and this is for arc volcanoes. But again, we show what all the melt inclusion data that have been collected in volcanic arcs. That's where most of the work has been done. And you see that there are large variations in water contents. The highest are like 7 weight percent, 5, 6 weight percent for the Mariana Islands, for example. And Indonesia, goes up to 6, 7% weight percent. Lesser Antilles even higher. Right? So we have a lot of data now, and it's clear that we have these high water contents. The lower water contents are probably somewhat degassed. Likewise, CO2 concentrations, 4,000 ppm, 6,000 ppm, are not unheard of, right? They have been measured. If I had given this talk 20 years ago, we would only have very, very few data, okay? And most of them, the highest would have been like 2,000 parts per million of CO2, because we just haven't had as much data, right? As we collected more and more data, melt inclusions, people found higher and higher CO2 concentrations in those melt inclusions. So yet, still, these are degassed for the most part. Many of them have lost their CO2 concentrations. Again, I'm just making the point over and over again that CO2 degasses deep, and that whatever we see coming out of a volcano is not the whole story. Okay. So we talked about this already. I don't need to talk about this again. And so even though we have all these different gases coming out of volcanoes, there's a few that we can measure continuously and remotely. And so what we have done with many collaborators around the world, Italian colleagues and South American colleagues, is to install these instruments on volcanoes that measure CO2, SO2, water, hydrogen in the plume continuously. And so you put it next to the volcano. This is Masaya, and you put it there. The plume gas comes up, and it sees that instrument, sees these sensors. Inside are infrared spectrometers, some electrochemical sensors for sulfur and H2S measurements, memory board and electronics. All these boxes here are called multi-gas boxes, and different labs put them together in different ways, the way they want. Now I think you can actually buy one of those things commercially made, and it's quite well established now, right? So these instruments are super helpful because you don't have to go to the source of the gas and collect the sample and take it back to the lab if you don't have a lab, right? So if you put this box on the volcano, you can get really interesting data. And that's what we did for 1 decade, the DECADE project, Deep Earth Carbon Degassing Project, funded by the Deep Carbon Observatory, and we published a bunch of papers on this approach. So it's very simple, right? And essentially, you can measure the CO2 SO2 ratio in this gas, and with pressure or depth, that ratio will change because the CO2 will degas first as the melt rises up. The CO2 has lower solubility. So if you take a hypothetical ratio of 1 of CO2 to SO2, as that magma rises, the carbon to sulfur ratio will go down because the CO2 is going out and the sulfur dioxide is still remaining in the melt more. So the melt is becoming depleted in CO2. And the gas will do the same thing. Now, of course, the gas is going to be much more CO2 rich because the melt this is just kind of schematic. But the fluid is going to be much higher in CO2 than the melt at depths. Right? That's what we talked about. We said at deeper levels, you're going to have CO2 degassing. And as that melt rises, this carbon to sulfur ratio is going to decrease. And then in the end, it'll be pretty low. So this melt will be very much degassed, and the carbon sulfur ratio could be less than. Okay. Whereas deep gas is going to be higher in carbon sulfur ratio because you're mostly degassing the CO2. Now, most volcanic gases have these ratios between 1 and 10. Okay, so you go to any volcano, you measure its composition, it's going to plot between 1 and 10. And so that means that most of the gas comes from relatively shallow levels. Right? So even though some of the gas may come from deep, most of it happens probably in pretty shallow levels. Now, if you just have your magma there and it degasses, and you were to catch everything, right, the ratio, the gas would do something like that over time. So let's look at some data, okay? Here is Villarrica volcano in Chile. This is an example that was published by Alessandro Ayupa back in 2017. I think it's the nicest example still to show this approach. Right, so here's time, 2004 to 2012. And these data points are people climbing up to the volcano, right? Climb up there and put the multigas there or collect a sample and plot it, right? Take it back to the lab. You have one data point. Carbon sulfur ratio of 1, 2004. This was during a workshop. There was an IAFSE workshop in Pucón. So Shinohara and Jeff Witter climbed up there after the workshop and collected this data. Then no data until 2008 or 2009. Georgina Sawyer went up there with an FTIR and collected another data. And then nothing again till Yves Mouzman went up in 2012, collected another data. Okay, so we have 3 data points over a time period of about 10 years. So that's the situation we are in if we just go there once in a while. Every few years, climb up, collect the sample, take it back to the lab, you get one data. You have no idea what happened in between. You have no clue. Right? It may be the same, it may have changed. We don't know. We just know it was the same here, about the same. So the ratio is about 1. Okay. So then, with the Deep Carbon Observatory in 2014, we installed the multigas instrument up there on top. And you see the ratios have a huge variability. Now, all of a sudden, we see that the ratio is really different from 1. Okay. And if you zoom in to that, it looks like this. So here's November 2014. That's when the multigas was first installed up there. And the ratio is kind of background, 10 or 1 to 2, maybe 3. So it's pretty stable. Here we have no data, probably too much snow. Then the instrument comes back. So it's measuring about background for a couple of months. But then we see this big increase in the ratio, right? And it's definitely real. Right? There's a factor of 10 increase in carbon to sulfur ratio. That's when you have increase in activity, you have more seismicity, you have just stuff happening at the volcano. And then there was the eruption that looked like this. So The increase in carbon to sulfur ratio, you can read the paper. The idea is that more magma came into the system that had more CO2 in it. And it essentially overwhelmed this background ratio of the magma that's at shallow levels. The ratio increased and triggered the eruption. Here. There may be a slight decrease in the carbon to sulfur ratio. This is pretty common. You have an increase when the magma first comes up, releases its CO2, it sits there, degasses, the ratio actually goes down in eruption. And so it's a beautiful example of how the gas composition changes right before an eruption. And it's a few weeks before the actual eruption. So that's one example. We have other examples from Masaya, from Poas, from Turrialba, from other volcanoes around the world, where the multigas is used to monitor the composition of the gas and where eruptions happened during that time. Now, of course, the eruption destroyed the instrument, okay, so no more data here. But once the eruption stops, you could go back up and put another instrument there and continue monitoring. Okay. Question?
Yeah, you were saying that more gas coming from the system than what the carbon dioxide is half.
Yeah.
Before, you present that there is inverse proportionality of magma flux and carbon dioxide flux. Before you present that,
Right.
When the flux have high flux of magma, you have low flux of carbon dioxide. What is this?
Yeah, I see where the misunderstanding is. So we go back to where I said that. Right? So this is what you're thinking. Is it this?
There is the graph presented in the morning. Say where we say that we have 4 megaton of carbon dioxide
Yeah.
as flux.
Yeah.
And
That
have
one.
small amount of carbon dioxide. I don't know if it is the same way. Yes, maybe. It's
Not this nice, nothing.
The screen is not being shared because you
Oh, yeah.
you were still down.
Oh, I see. Okay.
So we have to probably go back to the Zoom. Oops. Yeah, we share again.
I'm showing.
This one. Yeah, can eventually do this.
this way.
Yeah, this one, right? So yeah, that's what I thought you were referring to. So what this one shows us is that if I have a low magma flux, then the CO2 concentration has to be pretty high in the magma in order to produce 4 megatons of CO2, right? If I have a high magma flux, the CO2 concentration in the magma can be low in order to produce this gas emission. So if I have a magma emission rate that's really high, then I don't need to have a lot of CO2 in that magma in order to produce this flux of 4 megatons. Right? Because the magma is just coming up very fast. There's a lot of magma coming up. And even though the CO2 content of the magma is not high, it can sustain this 4 megatons of CO2 emission per year.
How do you rate the knowledge from this slide with the current slide?
I can't quite relate that, but the point of this, yeah, but it's related, okay? So we go to this. So this just shows you essentially the solubilities. Okay.
Someone put a comment in there, change the presenter view to slideshow so they can see. Yeah.
They can see? Okay. Yeah, so yeah. Right. So essentially, that slide that I'm going to show you is based on this. Right. So you have CO2 solubility, and I have water here. I don't have sulfur. Because sulfur is not as well constrained. It's getting better now. But anyway, water and sulfur are similar. Right. So if you have CO2, solubility is much lower, even at high pressure, than water. Right. Like sulfur. So CO2 is much less soluble than sulfur. Now, if you then go to this and you take a melt that has a CO2 to sulfur ratio of, let's say, 1 at 10 kilobars, 30 kilometers depth. So if I were to collect the melt, analyze the melt inclusion, analyze the CO2 sulfur content or ratio, it would be maybe 1. Okay. Once that melt degasses, it'll degas a lot of CO2. And the CO2 sulfur ratio will be very, very high. Right? So in order to relate it back to the other diagram, if you knew the CO2 flux, and if you knew the CO2 content of the melt, you could calculate the amount of you could if you know the CO2 flux, if you know the CO2 content of the melt, you could calculate the melt flux. Or if you know the CO2 flux and if you know the melt flux, you could calculate the CO2, right? But for this volcano, Villarrica, we don't know the melt flux at all. But let's say if you knew it, then you could make an estimate of how much CO2 is in the original melt. Right? Then you could say, okay, in order to get from a melt CO2 sulfur ratio of 1 to 1,000, I need to degas that much melt, right? That requires you to know the emission rate of CO2, which for Villarrica, we don't know, okay? So if you had that information, for some volcanoes, we have it, like for Etna volcano or Turrialba volcano, we know the CO2 flux, we know the sulfur dioxide flux, and we know the ratio. Then you can begin to say, okay, we have that much magma coming into the system to get the ratio to higher values. Right? So that's what that would require, right? If you know the flux, if we knew the emission rate here, and if the emission rate goes up and the carbon to sulfur ratio goes up, we could begin to make an estimate of how much melt needs to go into the system to produce the flux of CO2 that we measure at the surface. And in order to make the ratio go from 1 to 10. Right? But we don't know the CO2 flux or SO2 flux for that. And that's all often the case. Very, very few volcanoes do we have everything, right? We usually lack some information, like either the carbon to sulfur ratio or the SO2 flux or the CO2 flux. So there's always, there's only a few examples where we have everything. Really well monitored volcanoes like Kilauea get mass stromboli, those really well monitored volcanoes. They have pretty good continuous data, all of these parameters. But even if you don't have the flux, this is a very strong signal before an eruption. And it is very likely related to magma coming into the system. Okay. So it's very relevant for what we talked about at Lake Kivu. Okay. And yeah, that's exactly the end. So the next part will be the interactions of that magmatic gas with the water. How does that affect the gas ratios? Right? And Poas is a crater lake that can illustrate this process really well. But we could also think about Lake Kivu as a place where these processes would certainly happen. So we stop. Oh, chat. Okay. So changing. Okay. No questions. Okay, so I'm going to tell them when do we come back? 2 p.m. We break for. Okay. Cool. So should I just leave this on? All right, we are back from lunch, and for lunch we talked about this very nice series of data where we talked about how carbon to sulfur ratio can change right before an eruption. But it's really important to have a baseline, right? If you don't know what the baseline is, like the baseline of your volcano or your lake, then you don't know if you see a change, if that is really because of something is happening or because this is natural variation or what's going on. So that's why I always like to show this data set because even though we only have a few points here, 3 points over 10 years, we know that a value of 1 is more or less a baseline. And then as the instrument was put in here, we can see that now this data here is right on that baseline, right? And if you had put the instrument here and you see, oh, it's 8, right? And then you're like, I know the baseline, it has always been 1. So 8 is very high, so you would be very concerned. But if you didn't have that baseline data and you put in your instrument here in February 2015, and you measure 8, you'd say, oh, maybe that's normal for this volcano. Because there are volcanoes that have a value of 8 for carbon sulfur ratio. And then you would be very surprised if there's an eruption, just very soon after you put in your instrument. The point is having baseline data, no matter if you have a lot of data or just a few data points, is really important. And therefore, monitoring Lake Kivu like they're doing, collecting water samples, collecting gas samples over time is really valuable. Even if you don't see a change, at least you're establishing baseline. It's the same in geophysics, right? You have to have a baseline to see what the volcano is doing, how many earthquakes there are per day, what's normal for the activity. And once you see a change, then you can evaluate potential hazards. Okay, so we talked a lot about the magmatic component. And again, here we see that the magmatic component is really dominant, right? There's not much of a hydrothermal system. The volcano is just there. It's covered in ice, but there's no liquid water really interacting with the volcano or the gas at the surface. The situation usually is much more complicated. Now, when we have a geothermal or hydrothermal component in the volcanic system, it affects the magmatic gas. And so I always like to talk to my students. I always teach them about magmatic versus hydrothermal. Right? There are two different components of the system. And understanding the interplay between those two is really important and powerful because it can give you additional information. I'm going to illustrate this with some data from a variety of volcanoes. What we see here is a Poas volcano in Costa Rica that we've been working on for a long time. But it has, right now it looks different, but it used to have this big crater lake inside of the volcano. So here's the rim of the volcano, this is the crater. And you can see two people walking along the edge of the crater. Inside of this crater is another crater and it's filled with a lake. We call this a crater lake. And it's an acid lake. It has a pH of 0. Very, very acid, right? And the temperature at that time was maybe 45 degrees centigrade. It has a color of kind of greenish and has a lot of suspended sediments. It has a lot of little sulfur particles in it. And so clearly it's interacting with the gases that are coming up from the magma body. So essentially you have the magma body, magma is releasing those acid gases, and those gases interact with the lake water. Now, it has been. Excuse me. There you go. Oh, no problem. So yeah, in general, when we think about volcanoes and magmas, we have the magma at the bottom underneath the volcano, and the gases come up. But on the way to the surface, sometimes you have a lake in the way, right? So the gases will interact with that lake water, and has been known for a long time that these certain reactions are dominant in these systems. And there are many, many reactions that you can write, chemical reactions that you can write. But this one here is a very important one. And what we see is that we have the magma, and we talked a lot about CO2 and SO2 and water and chlorine and fluorine, all these gases coming out of the magma. And as they rise to the surface, they interact with this lake. So the gas reacts with the water, and the SO2 makes H2SO4 in the lake. H2SO4 is just sulfuric acid. And so this is the reaction that would happen. You have SO2 gas reacting with water, liquid water, makes H2S gas and aqueous, sulfuric acid. And so that is one reaction that is very, very common in these systems. Now, what you would see if you were to monitor this lake, or the gas that comes through this lake, you would not detect any SO2. Because if the reaction is complete, all the SO2, sulfur dioxide, would form H2S, and the sulfuric acid is in the lake, right? So the acid that's formed stays in the lake, stays in the water, and the gas, the H2S, would go through the water and degas from the lake. This is another reaction where you have this aqueous SO2 gas or aqueous reacting with the water, and you can then form elemental sulfur, right? S. Elemental sulfur droplets. And again, you're going to form this sulfuric acid. In this case, in this example, these two reactions, the SO2 would be transformed to H2S gas, and then it will also transform to elemental sulfur. And in Poas Lake, you in fact do see little spherules of elemental sulfur floating around, right? So we know that these reactions are happening. Now, at Poas Volcano, you have these fumaroles here, which are on the side of the volcano, of the lake. And these gases here are not affected by anything interacting with the lake. And so if you were to measure, if you put your multi-gas system here, you would get more of a magmatic component than if you were to put your multi-gas like on the shores over here, where you would get to see this gas coming off the lake, right? You would get different compositions depending on where you would put your instrument. And there is a very nice example, very nice data set about how the gas composition changes with changing activity at Poas Volcano, right? And we can talk about this later if we have a little bit more time. But what we see is that before eruptions of the lake, this gas composition really, really changes. It changes from being kind of a hydrothermal composition to being a magmatic composition. because there's so much injection of magmatic gas that this reaction cannot keep up. And the SO2 just streams through the lake, right? So the reaction can't keep up with how much SO2 goes into the lake. And you get this big pulse of sulfur dioxide before an eruption. So we can talk about this a little bit later. But let's talk more about the overall geothermal, hydrothermal system. Okay, so here we have, again, your magmatic input. And then you have, at some point, you have meteoric water coming into the system. Okay, so you will have a two-phase region here where you have water plus gas. And the water is from meteoric water, right? So the water is simply essentially rainwater, snow melt, lake water, and it interacts with the gas and it makes this kind of aquifer region. And at the in the crater area, you're going to have very acid fumaroles, right? So those will have the sulfur dioxide, the chlorine, the fluorine. And as you move away from the source, the gas composition and the water composition will change. The water composition will become more and more neutralized by interaction with the rocks. So for Lake Kivu, there's a big, big lake. The water source is meteoric water. And the gas input is happening, but the composition of the lake water is still neutral pH. So it's not acid. There's not enough acid gas coming into this huge lake to make it become acid like POAS. Okay, so it's more similar to this kind of system where you have this big lens of neutral water, you get some input, but the water itself does not reflect these acid gases coming into the system. Now, yeah.
Since we have a huge volume of carbon dioxide, why this hydrogen carbonate? Why it is not forming this acid hydrogen carbonate?
It's not enough to really make it acid, right? So you would have to have a lot more, I think, CO2 going into the lake to make it, to get the acidity down to the
lake. We needed the carbon dioxide a lot, or we needed this.
Well, in the gas, you measure CO2. So as soon as you bring the water up, it degasses and makes CO2. And if you then also measure the water, you would get bicarbonate. You could determine the amount of bicarbonate in that. And together, that would give you the total amount of carbon in the water. Right? So what we will do with our samples, we will, of course, measure the gas, and then we'll also measure the water and see, doing a titration and see how much bicarbonate there's in it. But I would think that most of the CO2 has degassed by the time you get it into the evacuated water. Now, relevant for rift volcanoes, you have these faults. And often those faults allow water to come down deeper into the system, into the hydrothermal system, right? So you have meteoric water recharge into the system, and that is going to affect the whole temperature distribution underground. And what these lines here are about are lines of equal temperature. So the magma is going to be really hot, right? It's going to be maybe 800 degrees or so. But even here in this region, you get areas where you have 300 degrees hot fluid, which is going to be a mixture of gas and water. And as I mentioned before, if you are looking to drill a geothermal well to produce energy, ideally you want to be somewhere where it's hot. right? You want to be close to the magma, but you're going to have a lot of acidity in this region. So usually what people do when they explore for geothermal, for energy, they go further away where they can still drill into deep areas with high temperatures, but where the water is much more neutralized. Of course, if you go too far away, the temperatures will become too low and you're not going to gain much energy. Again, this is a very nice paper from the Encyclopedia of Volcanoes that talks about geothermal systems. It's the same model, right? You have the magma, you have the magmatic fumaroles, solfatara, and you see these temperature lines. And I'm going to talk about how do we actually know these temperature lines. Okay. This is related to more of a tectonic situation. Again, you have these deep faults. So for example, in the East African Rift, around Lake Kivu, you would expect deep faults, extensional environment, and those environments would allow water to move pretty deep down into the system. And eventually it's going to get heated up and it's going to travel up. So you kind of form these convection cells underground, cold water coming in, getting heated up, coming up, flowing out to the side. And that's where you would get these neutral chloride springs, these CO2-rich springs away from the volcano. So it's a kind of a classic schematic of geothermal, hydrothermal systems. There can be complications if you have some geologic layers, impermeable layers that can affect the water flow. Okay, so knowing the subsurface is important to understand where the water goes, where the heat goes, and all these different interactions. So what's really important to understand is that this is just a model where you can see that as you add gas to the cold water, you will get more and more an increase in temperature, right? And so once you get here, you get into the volcanic environment, right? As you add above a certain amount of magmatic gas, you really get into the volcanic environment, meaning you're higher than 100 degrees C. So the water is essentially boiling. You get boiling fumaroles, you get steam vents close to the crater. When you are in an area where you have steam coming out of the ground, where the temperature is higher than 100 degrees, we can say, okay, we're in a volcanic environment. Whereas if you're in an area where you have liquid plus gas, then you're more in the hydrothermal environment. But the heat is transferred from the magma to the water by the gas. Okay. Now, globally, I don't have to spend a lot of time on this, but this is overall the geothermal area. This is a bit outdated, of course, now. But there's many geothermal plants around the world. Iceland, for example, Kenya has some geothermal plants, Ethiopia. All over the world, people are harnessing that geothermal energy. And here's just a list of how many megawatts of geothermal energy installed. The US is pretty high. That's because of mainly one geothermal plant, the geysers in California. See Philippines, Indonesia, Mexico. All of these countries are in places where we have a lot of tectonic activity, subduction zone, rifting, where magma is coming up to the surface, close to the surface, and providing the heat for these geothermal areas. Just some technical things. Essentially, you get water coming up, and then you have a steam separator. So the water boils, and then that runs the turbine. And then at the end of the turbine, you have essentially a vacuum. You condense that water again, and you get it into cooling water, cooling tower, you condense it, and you either re-inject it, right? So you re-inject it back into the ground, keep the pressure high in the geothermal reservoir, or you can use it for other purposes. There's different systems. vapor-dominated system, of course, in those systems, you already have steam. And the geysers is an example for that in the US. So you don't have to flash the water into steam, just run it straight through the turbine, condense it, and push it back in. That's the geysers, okay, up here in Northern California. Now, for example, closer to here, Volcanic fields in Kenya, over here in this part of the rift, we have Volcanic. Again, you can see these lakes that you might be familiar with, Natron, there's Magadi, there's Lake Naivasha, Nakuru, Bogoria, Baringo, and so on. They're all Rift Valley lakes. They're the faults. Volcanic is here. It's a volcanic caldera complex near Lake Naivasha. And again, complicated tectonics with faults and so on. But the temperature profile is very well established there. You see the temperature increases as you go down, only about 1 kilometer. You have very high temperatures. And you can see that once you have this installed, this figured out, you can figure out how deep you should drill in order to produce energy. Right? So here, for example, are different lines of wells that they drilled, and you can see a clear increase in temperature in all of these places, about 600 meters down from the surface. And we reach quite high temperatures there, up to 300 degrees C, right, at about 2,000 meters depth. So you only really need to drill a couple of kilometers, and you already reach very high temperatures in the system. And this is a very nice diagram produced by Shi et al. 2021 of the Volcanic system. We have the geology here, and here is all where you have all the high temperature fluids interacting with the rocks, and that's essentially the reservoir where the geothermal energy is produced. Now, for the geochemistry, for the gases, it's a very, as I already explained before, that high temperature fumaroles like these, high temperature volcanoes, temperatures 1,000 degrees to 500 or so, we see that they're rich in CO2, in SO2, not some H2S. But for example, the hydrothermal fumaroles, they have no SO2, right? And they have high H2S. And they have no HCl and no HF. That's because the SO2 reacts with the water, making H2S. And the HCl from the magmatic gas, it just dissolves in the water. So HCl partitions very rapidly into the water. So for example, Lake Kivu, even if you have a high temperature magmatic gas coming into the lake, if you were to sample the gas, you wouldn't see any HCl or HF. And I don't know if there's a lot of chlorine or fluorine in the lake water. I don't know. You would see H2S, and maybe that's what we see. The smell we smell at the Lake Kivu is H2S. Is it from the magma? Is it converted from SO2? Or is it some organic matter? We don't know yet. We have to do some analyses. We can find out. Now,
Yes, so seeks the H2S to CH4 and other hydrocarbons.
yes, it can be a product of organic breakdown, decay. Right? So that's another source of H2S. And if you have organic matter in an anoxic environment, like at the bottom of the lake, you can produce H2S as well. And we will be able to hopefully analyze some sulfur isotopes to figure out if all the sulfur is from that process or if there's actually some magmatic. Now, one of the uses of gas geochemistry, and I think we could even apply something like that at Lake Kivu, is to figure out what are the temperatures. As I showed you before, those diagrams where we have the nice temperature lines of the geothermal systems, how do we get those temperatures? It's actually from gas geochemistry, right? And it's an approach that's shown here in general, you can use gas ratios, for example, CO to CO2 or hydrogen to water, and thermodynamic models allow you to write reactions between these components and these components, and at what temperatures these reactions are in equilibrium. So as the gases come to the surface, they often freeze in that equilibrium. So even though the gases move from high temperatures to low temperatures, you sample them at the surface, maybe at 100 degrees C, what the gas has seen at depths is hotter than that. And so the composition is in a sense frozen in, and you can then do the calculation and plot your compositions on these kinds of diagrams. And so all of these points here are from geothermal systems around the world. So this is all from Italy, for example. These are from other places around the world where people have collected samples, and then you analyze them, and then you can see what the temperatures are at depth. And whether you have a vapor composition at depth or a liquid composition, or if you have a mixture. Right? So, for example, if you take this data point here, L, that's Lardarello in Italy, you would analyze, you collect your sample, you analyze the CO-CO2 ratio and the hydrogen-water ratio, and then you use this diagram. You plot it, okay? And you would see then that the temperature of equilibrium of this particular gas was 250 degrees. So even though the temperature at the surface that you sample the gas at might be 100 degrees or even less, it tells you that at depths we have 250 degrees. Now, we don't know at what depth exactly that is. We don't know. That's the geothermometers can't tell you that, but they tell you that we have higher temperature at depths. Likewise, if you went to go to this one, PEH, for example, Philippine sample, the temperature below the surface is 350 degrees, very hot. Okay? That's almost, supercritical fluid. However, if you are over here, G, for example, Guayana in Ecuador, you will only have 200 degrees below the surface. So the geothermometers are a tool to tell you something about subsurface temperatures. And perhaps this is something we can try even at Lake Kivu, to analyze the samples that we collect and do some of these calculations. We can say something about the temperature below the lake, where these gases are coming from. This is the same style of application done in the Magadi Natron Basin and in the Kenya Rift volcanoes. So here's Lake Natron, here's Lake Magadi. My former student, Jungwoo Lee, PhD student, did this work. So here's Oldonyo Lengai. We sampled these places. And then they're plotted over here. This is a slightly different geothermometer. Again, you have ratios methane, CO2. So for example, Lake Kivu, we could easily try this, right? We have methane, we have CO2. If we have hydrogen and argon, and using these grid lines, we can plot the data. So for example, Kenya Rift volcano fumaroles plot here. So that means the temperature is 250 degrees at depth. Even though the outlet temperatures might be 100 degrees, we know at depth we have higher temperatures. And then some other places, different springs, Rungwe volcanic province, data are shown here. Again, we can get an idea of what the temperature is below the surface. Classic caldera system is in New Mexico, Valles Caldera. Again, I'm just showing this to illustrate the general idea of how these geothermal systems work. You have a high temperature part here in the resurgent dome, for example. You have acid fumaroles, acid springs, water comes in, meteoric water comes in, and you have these outflow zones. the water travels, you deposit perhaps some travertine in places, and you can produce these models of what the subsurface looks like based on the geochemistry of the gases. So that's the system. You see, for example, this is Valles Caldera, this is the caldera rim, this is a resurgent dome. These are rhyolite domes that erupted after the caldera forming eruption. The details are not important, but water, meteoric water comes in here on the side, and here you have the outflow zone of warmer water to the south. So again, there's a huge amount of literature on the geochemistry of hydrothermal systems, neutral chloride waters, and you have different compositions. You have pH that's between 5 and 9, for example. You have the acid sulfate cap zone, where you have higher temperature fumaroles. You have acid conditions, right, like this, and you get very different chemistry from the outflow zones. Again, we can look at the different areas, right? So pH can be very, very low, close to the source. You have very high sulfate. As you go away from that magmatic source, the pH becomes neutralized. Sulfur usually goes down. Chloride might go up. And so you can identify where you are in the system in that way. Likewise, you can use water chemistry to get an idea about the deep temperatures. So for example, you have these wells from, this is also Valles Caldera in New Mexico. You can analyze the sodium, potassium, magnesium, and you can use these diagrams to figure out what the deep temperatures are. 300 degrees, and that's consistent with what they have found during drilling in those areas. So the point of all this is to show you that geochemistry, water and gas geochemistry can be used to figure out what's happening below the surface. So you have the magma body, but then you have this whole hydrothermal system in between, and the gases and the waters interact with that, and the gas chemistry and the water chemistry tell you something about those conditions at depth. So it's an exploration tool for geothermal energy, but it can also be used, for example, for a monitoring tool, right? So for example, if you were to collect samples of a fumarole that's affected by hydrothermal, and you do the geochemistry, and you get the temperatures, and you can see a change in the temperature, maybe that's due to heating up of the system, maybe that's due to increased magmatic gas into the system. So those are some of the tools that we can utilize and that have been utilized in systems like that. Okay, yeah, so we've already talked about this. This diagram here, I just show this classic diagram, right? These are isotopes. Okay, so we have, this is water. So you sample the water, H2O, and you do the isotopic analyses of hydrogen in that water and the oxygen. And this is plotted against SMO, standard mean ocean water. The point is that here's the meteoric water line, right? So any surface water that you would plot, that you would collect in the world, would plot on this line. So maybe rainwater, some lakes, some rivers, all around the world would plot along this line. And then what has been recognized a long time ago by Harmon Craig was that these geothermal waters, they're all shifted towards higher or heavier oxygen isotopes. So for example, we have Yellowstone National Park, we have Lassen, we have Salton Sea, we have the geysers, Lardorello that we talked about. All of these waters are shifted to heavier oxygen values. But essentially, they're meteoric waters that have interacted with the rock, with the silicate rock, and have exchanged the oxygen from the SiO2, the silicate rock, and therefore have been shifted to higher values. And what we interpret this to mean is that the source of the water is just meteoric water. Okay, it's just surface water that is heated up, that's moving into the system, interacts with the rock, and then takes on that rock oxygen isotope composition. Therefore, the water that we see in these geothermal hydrothermal systems is from the surface. There's no magmatic component. Now, what Werner Gegenbach showed a long time ago is that if you have really high temperature fumaroles, they show a shift towards heavier oxygen isotopes as well as heavier deuterium values. And he proposed that this is due to mixing with a magmatic water source. So those are some of the details that we don't have to go into. But essentially, what it means is that the water in low temperature systems is of meteoric origin. If you go to high temperature systems, then perhaps you could get that magmatic component of water that comes from the magma that we talked about, the water solubility, degassing from water, from magma, producing those compositions. Right, and that's kind of shown here. Like these low temperature systems are shifted like that. High temperature systems like Vulcano, like Pacaya, so on, might be shifted on St. Helens to these different components, to a different end member. This could possibly be the magmatic water coming from the magma itself. So just to kind of summarize, again, going back to our diagram, we talked a lot about the magmatic component. Right? We can get the composition of the fumaroles, and we can get melt inclusions to get information about how much CO2, how much water, how much sulfur is dissolved in the melt. And then we have the surface component where we have water originating from rain, and that is interacting with these gases. And we get CO2 in both cases, right? But we have hydrothermal fumaroles, hydrothermal component. We have volcanic components. Hydrothermal components usually have less sulfur. Volcanic components have higher sulfur concentrations in the gases. Okay? So those are, in essence, the end members, the magmatic versus the hydrothermal components in volcanic systems. I was going to move to the next part 3, but before we do that, are there any questions about this kind of hydrothermal magmatic interplay? Okay, so the third part, probably wondering how many parts are there? Well, there's the third part, and then there's one small other fourth part. Okay, so we're almost getting close to having more of an open discussion. Yeah. Oh, the salinity for
higher concentrations. Because they share, they have very high salt content, or the salt content was 0.
You mean for the gas geothermometers?
Yeah.
Yeah, that is just based on gas reactions. And the salinity of water is not considered at all. Yeah, not considered at all. In those examples. Yeah, that's a good question. Yeah. But what they do is, and these gas geothermometers have been used for a long time. And I've just shown a few of them. But for example, Icelandic researchers have done a lot of work on using gas geothermometers and then comparing them to drill cores or to drilling and measuring temperatures that they see at depth. So the matchup is usually quite good. It's not exact, but it's a pretty good match. So we think that those geothermometers give you a pretty good idea, you know, plus minus, I don't know, 20, 30 degrees, maybe 40 degrees or something. But it gives you a pretty good idea, because otherwise you can't know what the temperature is. There's no other way. Perhaps some geophysical surveys, magnetotellurics or something like that, perhaps. So it's the best we can do. Yeah, that's a good question. So I'm going to talk a little bit about the tectonic part. And that's really also related to the East African Rift, where we have done a lot of work on this aspect, right? And so this diagram is something we put together, and it shows you just kind of the significance of volatiles in all of these places, right? We have the convecting upper mantle, we have mid-ocean ridges, right, where we have magma moving up to the surface, mantle moving up to the surface, melting, producing magma. And what we see, those numbers here are just emission of carbon, right? And then we have subduction, right? So we have subduction zones. Some of the sediments go down, bring with it the carbonates, the organic carbon, and other materials. And our volcanoes bring those gases back up to the surface. Now, in rifts, we have this very big cratonic sublithospheric continental mantle lithosphere, and we might get influx of materials from plumes or from other sources. But in the end, you know, you also have emissions of gases back to the surface. So it's just showing you this again. So we have mid-ocean ridges, we have plumes, we have subduction zones, and we have continental volcanism. And all of these components of the Earth system have influence of the mantle somehow, right? So mantle here, you have the lithosphere, subducting plate, you have the continental crust, and all of these parts contribute to what you see at the surface, coming out at the surface in terms of the magma composition, but also in terms of the gas composition, right? So this diagram shows us again that we have, you know, the core here, we have continents, we have subducting slabs that might penetrate all the way down the deep mantle, and you have ocean ridges. You know, material is moving around very, very slowly. Of course, we need to remember that all of this is solid state, right? And there's no like blobs of magma floating around underground. So it's all solid state, solid rock. And it's moving very slowly. And as we talked about before, as things move up, those things can start to melt and degas. So gas compositions, in terms of the big tectonic picture, reflect those processes, okay? So when you look at nitrogen, helium, and argon, those three almost noble gases, those of course are noble gases. Nitrogen is like a noble gas. It doesn't like to react very much. You can see that in places like the rift, continental rift, we have compositions that are lying along this, in this triangle, right? So here's air saturated water, and here's helium, mantle-derived helium. So all of these samples from Magadi, Natron, Kenya, Odolengai, Rungwe, Dalol, which is in up north in the ICTP-EAIFR, Eagle Rift is in Europe, Colorado Plateau in the US, they all lie in this kind of field, right? And they're very different gases than what you see if you were to sample subduction zones. If you sample these gases here, they would be plotting up here in this region. They have much higher nitrogen helium. And we think that this is because nitrogen is coming from the subducting plate. So organic material is breaking down and contributing nitrogen that then we see in the volcanoes, and that adds to that high nitrogen helium emission. In continental rifts, we don't have that, okay? Well, this is not very good drawing, but continental rifts are usually far away from subducting slabs, and so you don't get that additional nitrogen contribution. So the point is that the gases reflect even the bigger tectonic environment. Now let's talk about helium isotopes. Some of you probably know this already, okay? But I'm going to give you a short crash course on helium isotopes. And this is quite important. Geophysicists, they love helium. It's relatively straightforward to compare to some of the geophysical observations, because geophysics often tells you about mantle melting or the source of the magmas, where they're coming from, how deep, and helium can tell you something very similar. And so trying to match up those two geochemical and geophysical informations is sometimes very, very powerful. Right, so what we need to understand is that helium has two isotopes, okay, helium-3 and helium-4. And helium-3 is primordial. Helium-3 was produced when the Earth was formed, and it's not currently produced anymore, except for very, very small amounts. Anyway, it's not currently produced anymore. Helium-4, on the other hand, is a radioactive decay product of mainly uranium and thorium. So you have two isotopes. One is currently produced by decay, and the other one's not produced at all. And helium-3-4 ratio, that's the ratio we measure. And we express that ratio as a ratio relative to air. Right? So if I were to collect an air sample here and analyze it in the mass spectrometer, the helium-3 to 4 ratio would be 1.4 times 10 to the minus 6. So we have 1,000,000 times more helium-4 than helium-3 in the atmosphere, right? So you gotta have a pretty good mass spec to measure that. It has to be able to resolve a difference of 1,000,000 in terms of the abundance of these two isotopes. So it's a big machine, and the measurement is not easy. But we just say that this ratio is 1, just to have an easier conversation. So we express everything relative to air, all right? And so the cool thing about the helium is, first of all, it's a noble gas. So it's not going to react with anything. It's not going to care if there is a crater lake, if there's a hydrothermal system, if there's a Lake Kivu, if there's nothing. It's going to not react with any other thing. It's noble. Okay, so it just makes it to the surface, like clean, right? It doesn't care what it goes through. So that's why it's such a powerful tracer, right? So in principle, you could see helium coming out from a hotspot, from a plume, and that would reflect something happening down here. You might see helium that's affected by something like this, and you can trace processes that are really deep in the mantle. And so this we already talked about, right? So that's again, expressed in a little bit different way. Helium-3-4 ratio, helium the sample, 3-4 the sample, helium-3-4 of air. And these different areas have different signatures. So air has a signature of 1, because that's what we say it is. Air is 1 Rn. Crust is going to be 0.01 Rn. So it's much lower than air, because it has mainly helium-4 in it. There's no helium-3 contributing to the crust. So the ratio is lower than air. Now, mid-ocean ridges, with a mantle that produces mid-ocean ridge basalt, has 8 times the air value. Right? So 8 Ra, very, very consistent across the upper mantle, across mid-ocean ridges. Always 8 plus minus 1 Ra. Subcontinental lithospheric mantle, like we're dealing with here in the East African Rift, has about 6 Ra. So it's lower than MORB, but it's significantly higher than air and significantly higher than crust. Plumes come from very deep, and they have more than 8 Ra. So the highest ratios that we can measure, that we have measured so far, at least in geothermal fluid, is in Iceland, for example, 25 Ra. Okay. So very, very high helium-3-4 ratios. However, the dominant isotope is still helium-4 because, it's 1.4 times 10 to the minus 6 is Ra. So even if you multiply that by 8, it's still helium-4 is the dominant one. So all of these measurements are difficult. And here's some real data, right? So we see mid-ocean ridges, 8 Ra, and continental hotspots are all over the place, can be high, can be low, depending on how much interaction with the crust. And then here's some other hotspots and so on. So we have these clear, relatively clear signatures of different components. Most arcs are here. And now the problem with all of this is that you can have air contamination. So if you have an air value of 1, that would be plotting right here. And then you have to know if your gas here, for example, is just air contaminated, or if that ratio is actually 1. Okay. So is 1 due to a mixture of crust and mantle, or is it just air? And in order to know that, you need to measure the helium-neon ratio at the same time, right? So helium-neon ratio versus helium isotopes, helium-neon of air is about 0.3, would plot right here, right? That would be air. And as you move into that direction, you are reducing the amount of air contamination. So for example, these values here, hang on, let me see, no. So these are two different, here, Iwo Jima and Hakone volcano, right? So here's Hakone volcano, and Hakone volcano ends up being at about 9 Ra, okay? At the same helium-neon ratio as Iwo Jima volcano. And so Iwo Jima volcano has a helium-neon ratio of this sample, about 10 or 12 or 20, and helium-3-4 of 7. So you know that this difference between this one and this one is not due to additional air contamination, but it is real because they both lie far away from that air contamination. Does that make sense? Kind of. So knowing the helium-3-4 ratio is not enough. You got to measure helium-neon ratio in order to assess and correct for air contamination. Now, again, looking at the East African Rift, the study that we did there, we see a very large variation in helium isotopes. Right? Again, we have air-saturated water or air over here, helium-neon over here, and here's Magadi, here's Natron, here are the Kenya volcanoes. So for example, if you go to Magadi, all these values here are about 2 Ra, 3 Ra. Some of the Kenya volcanoes, they're up to 8 Ra, 6 Ra. Some of those guys here, the blue ones down here, they are very low. So they're actually crustal. And so you can very easily calculate how much crust contribution you have for each region. So these samples here, when they sample subcontinental atmospheric mantle, versus these samples here, they probably still have a mantle input, but are mostly affected by the crust. And many helium isotope studies have been done in Iceland. And in Iceland, you see that you have very high ratios. Here, for example, 26, 21, 24. As you go north, you get to lower ratios, 10. And as you go over here, you get even lower ratios. So there's a large distribution, large variation of helium isotopes in Iceland that has to do with where the plume is. So for example, that's what I was talking about. You overlay the geophysics. So here's the plume, the signature of the plume, S-wave tomographic image. And you see these deep components, these deep deviations from the mantle, surrounding mantle. So the idea is that you're bringing up material from very deep, 700, 800 kilometers, that's rich in helium-3, and then you end up with these high helium-3 flow ratios that you see in Iceland. Whereas once you go along the mid-Atlantic ridge, the melting, the contributions of volatiles and melts and so on is from the upper 150 kilometers, and therefore the helium-3 flow ratios along these would be 8 Ra. Okay. Any questions? Okay, so now helium-3 flow ratios, as I said, is a noble gas, and even if you have an old magma, the amount of helium that grows in from that magma into uranium and thorium decay as that magma sits around has a very small effect, right? You need to wait quite a long time, like over 1 million years or so, to in fact affect any of the helium isotope composition. So it's a very good tracer, okay? And again, we see variations in helium isotope ratios, and we think that this is just due to contamination of the crust. And so as the gases sit around in the crust, they assimilate some of the crustal helium that's produced that lowers the ratio in some places. So crustal thickness can have an effect to some extent on the helium isotope ratio. Right, and there's a lot of work that has been done on this volcanic front, Japanese arc, and you have ratios that go up to 8 Ra. So right there at the front, and this is due to contribution from deeper parts in the system. Okay, are there any questions? All right. So I'm going to move a little bit to other isotope systems, for example, carbon, and it just follows along on the helium. It's again used to trace the source of the carbon. Here we use the delta notation, right? So delta 13 of the sample is the 13-12 ratio of the sample, reference -1 times 1,000. So it's just a notation. So what we can do, and this might be something interesting for Lake Kivu, if you were to monitor it, you could potentially see a change in carbon isotope ratios with degassing. So you have a magma here, and the magma degasses CO2, and as the fraction of CO2 in the melt decreases, the carbon isotope ratio will change. It'll become lighter and lighter and lighter, right? And so, for example, if you were to sample a gas that has a carbon isotope -6 one time, and then you wait 20 years, maybe it would be over here, right? So you could potentially track the amount of CO2 degassing from that melt using carbon isotopes. So that's one application of carbon isotopes. The other application is the sources, right? So here we're combining carbon helium ratio. So this is a CO2 helium-3 ratio from the gas versus carbon isotopes. Here would be the mantle contribution, composition, and here would be limestone or sediment or organic sediments. So if you collect a sample that plots right here, then it's likely going to be a mixture of mantle gas mixed with sedimentary organic material. And so for Lake Kivu, perhaps maybe we can't do the helium-3, but with carbon isotopes, we can see how far we are away from the mantle composition, and that could be due to carbon being contributed from the breakdown processes that you mentioned. Calcite precipitation also affects carbon isotopes. I'm not gonna spend too much time on that. But this technique has been used a lot to figure out the contribution of carbon from the mantle versus the contributions of organic material. You can calculate this very, very precisely with this equation. Been done for a long time, like 30 years. Very, very established technique in geochemistry. Any questions about that part? Okay, so now I'm just going to go talk about CO2 flux. We talked about SO2 being monitored by satellites. CO2 is much more difficult. You can't measure it precisely enough using satellites so far. Maybe in the future we'll be able to, but so far we cannot. And one way of measuring CO2 flux is essentially this way, where you this is caldera. This is Campiflagray caldera in Italy, and essentially you walk around all these dots here. These blue dots here are hard to see, but you walk around. You make measurements of the CO2 emissions from the ground, and then you use ArcGIS to extrapolate, and you get maps like that show you the high SO2 fluxes in some areas and normal SO2 fluxes in other areas. And often the high CO2 fluxes are focused along faults, okay? And what you can do as well is to collect a sample, a gas sample, and analyze the carbon isotope composition. And in this case, we see that where we have the high CO2 emissions, like for example here, the carbon isotope compositions are quite magmatic. Whereas in areas where we have low CO2 emissions, like for example here, the carbon isotope composition are organic, right? So in this case, the CO2 is just due to decaying of organic matter, versus in this case, the CO2 is actually magmatic. It's coming from the magma. How do you make these measurements? Actually quite easy. You have this handheld system. It's called an accumulation chamber. Has an infrared sensor inside. This is work that we did around Oldonio Lengai. Has an infrared sensor inside. There's a little accumulation chamber here. You just put this on the ground. You wait 2 minutes and you get a CO2 flux measurement. So relatively quick measurement, but you have to walk around and you have to make all these measurements, right? It takes a while. And I've done this, for example, even in Antarctica, right? It's a lot harder there, but you can essentially make measurements like that anywhere. So then you can collect the isotope sample, and this is for Magadi natron area, and here's the carbon isotopes. And of course, the samples are going to be a mixture between air and the source composition. And what we do is this typical mixing plot where we plot 1 over CO2. So air would be over here, 450 ppm, and pure CO2 would be over here. So if you have a data point somewhere here, you just assume it's a mixture between air and the pure CO2, and you can extrapolate to what the composition is. And in this case, it's about the mantle composition. If you were to plot down here, then you have a significant biogenic contribution. So again, you can identify what's the source of the CO2. Are you actually measuring mantle CO2, or are you just measuring superficial decay of organic material? This is a delta ray instrument that I've used for these analyses. It can be transported all over the world, and you can analyze these data very quickly. So for Natron Magadi, we did this work, and here again we have faults. So this is the Magadi Natron Basin, deep faults. We have some earthquakes here, and we did a bunch of transects and measurements of CO2 in this area. It's all published in Kyung-Woo Lee's paper. But what I wanted to highlight is that we talked about this at lunch, that we have a fault zone, for example, and the high CO2 fluxes tend to be along the fault, right? So we see not everywhere along the fault do you have high CO2, but you have these kind of hotspots where CO2 is really dominating, where it's coming up along a fault. And when we collect a gas sample and analyze the isotope composition, again, close to the faults, we would see the strongest mantle contributions. So, how do I fit the line?
Yeah, so how do we get that line extrapolated from the data, the cluster, all the way and classify it as biogenic, and this one is mantle. How's the line that comes to is better? Is it in relation to the inverse ratio of carbon dioxide concentration?
Yeah, it's just the relation of the CO2 concentration in the sample.
It's very far away with the delta value, and it's coming from air.
Yeah, so this would be air, which would be about 420 parts per million. So the ratio would be this, a high number. And then as you add CO2, it would go that way. So it's just a linear mixing line. And this line here, I just drew from this point down here. I just drew that to illustrate that biogenic contribution.
It falls all the way.
Yeah. Yeah, so these samples here, they are a mixture of air, mantle contribution, and biogenic. These samples are kind of outliers, so maybe you could draw another line like that. But in these diagrams, but people use these diagrams all the time. You could get very detailed. You could say, okay, I'm going to explain this data point. Maybe that's a mixture of air and this composition. So anything that's kind of below mantle can have some sort of biogenic component to it. And the reason it's all mixed with air is because we use this accumulation chamber, which is full of air. And then CO2 comes in and changes the composition. That's what you get when you make the measurement. You get a change in composition of CO2 over time. And from that, you calculate the flux. But you also collect a sample, and that sample is going to be a mixture of the gas coming in and what's already in the chamber. Okay.
Yes.
Yeah.
Using those schools of carbon dioxide are among the faults. But those two spots.
Yeah.
What information can we get related to the magma propagation of the magma location?
I'm not sure if you can get any information directly. This has just been measured one time, right? So we went there back in 2013, and we collected this data, and we found, okay, there's an area where we have a very high CO2 flux. And then we have this area of high CO2 flux. But is there a magma down there that produces this? And there's no magma here? I don't know. We don't know that.
I was thinking that because
Yeah.
I was thinking that have a line of carbon dioxide instead of having spot.
It's never a perfect line. There's always areas where you have more emissions and less emissions. That's just the nature of, I think it also has to do with the fraction network, maybe slightly different lithologies along the fault. Perhaps some areas of the fault are more active than others, right? This is a pretty small area, it's only 500 meters, but perhaps parts of the fault move and parts of the fault don't move, okay? Or have moved in the past and not moving now. So there's probably a lot of different factors that affect exactly where the high CO2 is being located. But what we have found is that the highest fluxes are always related to faults. If you walk away from the faults, the flux really drops down. I don't know if I have a picture of that. Probably not.
Surface.
Only on the surface
You cannot imagine doing this the bottom
of the lake. I think we'd have to think about how to do that.
because it would be very interesting,
Yeah, it would be very interesting.
especially because we have the sediments.
Yeah. I think, with the eco sounders, perhaps, and they can visualize the bubbles, and maybe there's a way of doing it that way.
Yeah, but I'm not sure they measure the flux.
I don't think they measure the flux.
Exactly. So
Yeah, they just look, here it is.
Yeah.
But they don't tell us how much is coming out. But I think Ben's hydrophone, they can maybe measure the flux, but it gives you an overall. So it's I don't know, I'm not sure. On land, it's much easier.
yeah,
If we can walk around with that instrument. Okay. Yeah. All right. So, the idea, this was the modest. I love this acronym. So this is the Tanzania Craton. Here's the Manyara Basin. Here's the natural Magadi Basin. And this is the model we came up with. So you have high CO2 emissions here. You have helium isotope compositions that are mantle derived. And once you get onto the craton, the CO2 emissions really go down to almost nothing. And you have crustal CO2 degassing. Carbon isotope composition changes, it becomes crustal, and it becomes crustal. So, the craton does not allow any CO2 to come out. All the CO2 seems to come up on the sides of it. And that's where you produce all the melting. We talked about deep melting due to CO2 addition, shallow accumulation of magma chambers, magma bodies, lots of faulting, CO2 comes along those faults. Once you get onto the stable craton, all of that just stops. And you're dominated now by low CO2 emissions, crustal CO2, no more magmatic input. So again, total CO2 flux, not really topic for this audience too much, but we have a pretty good idea now of how much CO2 comes out of the East African Rift and how much comes out of ARCs, how much is diffused. Still a lot of error bars and variations, but we're getting closer and closer to understanding the whole global CO2 budget. All right. Any questions before we talk a little bit about some practical aspects of doing this stuff? We're doing good. Okay, so where the rubber meets the road, right? Actually doing this, right? I'm just standing here talking about data, and data have been collected over decades, many researchers around the world to come up with this picture that I presented to you of the different techniques, the different interpretations, what we can do with volcanic gases, what we can do with melting fusions. Okay, all of this is a background of actually doing something. And so what are the practical aspects? Okay, so if you were actually to do this here in Rwanda, it would be possible. It would be not impossible. It would not be easy. There would be a lot of barriers, but all of these barriers can be overcome with expertise, with hard work, and with a little bit of money. But the money is not that important. Money is actually not important at all. Because the most important thing is that you have the will to do it. If there's no will, I can throw millions of dollars at you and you're not going to do anything. Okay? So the most important thing is that people really want to do it, to really build up this capacity. The money will come. Okay, that's kind of how I see it. So, so first of all, you can collect samples like this very easily. right? I mean, not super easy, but if I took you to this place and teach you how to do this, in 2 days, you would know how to do this. No problem. It's not rocket science, okay? I can do it. So if I can do it, you, right? So what you need is this kind of bottle, right? And this is just a glass bottle, and you can buy this bottle. And you just need to evacuate this bottle, right? You have to have a vacuum pump, and you pump on it. So you evacuate, get all the air out. And then you may want to put some sodium hydroxide into that bottle before you evacuate it, right? So if you have sodium hydroxide in this bottle, you can absorb all the acid gases, sulfur, CO2, chlorine, fluorine, and so on. And then in the headspace would be all the other gases. When you take that bottle back to the lab, you can do the analysis. And you would take this solution and you would analyze it for with titrations, chemistry titrations, for CO2, for sulfur, for chlorine, so on. Okay. So then the headspace gas, you would use a gas chromatograph. Right. So this is what we did at Lake Kivu, right? So what we did is we just had this long tube that we lowered down with a weight to the bottom of the lake, and or to 300 meters, 400 meters. This is 500 meters of tubing. We went down to a maximum of 300 meters. And we have this water pump here. So we put the tube down and we pump. We calculated how much water we need to displace, 2 liters per 100 meters. So we just measure how much water we're pumping. And then after, like if we put it down 100 meters, we pump for, I think, 4 minutes. And then we collect this sample. So essentially, we have some plumbing here, very simple. We close off the pump, and we have a syringe here. So I suck the gas into the syringe to essentially clean that line, okay? And then essentially just collect the sample, right? So just open this bottle, and the water plus gas goes into this glass sample bottle, right? And then from this is a complete composition. I collect everything. I collect the water and I collect the gas. And then in the lab, I will weigh the bottle and see how much water I have in there. And then I'm going to analyze the gas here, going to measure the pressure of this. And then if I have the volume of the water, I have the pressure here, I know the volume of the bottle, I can calculate exactly how much gas and how much water I have. So we will know how much water, how much gas is dissolved in the water. And we can then analyze the water for carbonate as well and get the complete composition. Now, how to do the analyses? 1989, right? So that was, Gegenbach and Gogol published this report. It's a very long report. It has the complete collection and analysis technique for volcanic and geothermal. Now you understand the difference, geothermal and volcanic, right? Different techniques, slightly different techniques, but very well established techniques. Okay, published in '89. So describing exactly the sampling protocols for deep pool, shallow pool, for fumaroles, cool the sample bottles, and so on. Then you do the analyses. For example, if you have sodium hydroxide in here or not, you can do the alkalinity titration that you might be already familiar with. Maybe you did this in high school, where you just titrate with chlorine and a chloride solution and go from pH. Well, you start here maybe, but you go from pH 8.3 to 3.8, and based on this reaction of the acid with the sodium hydroxide with the CO2, you can calculate how much CO2 is dissolved in that water. And you can do a similar thing for sulfur, you can do a similar thing for chlorine, and so on. Everything's described in that book. Now, the headspace, you have to have a gas chromatograph. And the easiest gas chromatograph is shown here in this diagram that was put together back in 89. In fact, it's two gas chromatographs. Okay, and I don't want to go into huge detail, but here's your sample border, and here's one gas chromatograph, and here's another gas chromatograph. One gas chromatograph has argon as carrier gas, and the other one has hydrogen as carrier gas. And then you just have a couple of different columns that separate the gases. And so on this side, you analyze everything that's not argon, because you have argon as a carrier gas. So you cannot analyze the argon in your gas sample because it's the carrier gas that pushes the gas to the column, right? So if you want to know argon, you have to have another gas chromatograph that has hydrogen or helium as a carrier gas. And therefore you can get, by having two gas chromatographs, two detectors and two columns, you can get the complete composition of the gases. There are other ways of doing it that are more complicated, but this would be like the easiest way to start. Gas chromatograph systems, pretty cheap. I don't know, you can probably get one for $20,000. That's the cost of a seismometer, maybe.
So it's too much.
So, with the argon being the carrier gas in the space, if you want to enter the baseline and say this is argon signal, this actually becomes the barrier constant.
Yeah.
But anything beyond my baseline, but this particular mass to charge ratio could be from my sample. Is it possible to do that action?
Yes. So it's not a mass spectrometer. And the gas chromatograph is essentially a column. And the column is like a sieve. So the
detection is not mass.
No, the detection is not mass. The detection is a change in thermal conductivity. So it's called a thermal conductivity detector, TCD. It's a TCD. So it's a wire, right? And so the carrier gas flows over that wire and gives you a certain voltage output, right? Yeah, it'll be your baseline. And then your column is like a sieve. We call it a molecular sieve. And each gas component has different size, and it has a harder or easier time to go through that sieve. Retention time, right? And so as you get, for example, hydrogen will go through very quickly. And so all the hydrogen will go through and it hits that thermal conductivity detector. So it's going to be a mixture of hydrogen and argon. And that's going to change the thermal conductivity of that wire. And that's going to make your peak. And then the next gas will be nitrogen coming out, right? So you get a signal from the nitrogen. So the thermal conductivity detector doesn't know that it's argon or nitrogen or whatever. It just sees the deviation due to the mixture. So as you add more nitrogen, your peak will get bigger.
One last thing is the GCMS.
Yeah, GCMS, much more complicated. But you have a GC where you have a column. So you separate the different components and then you put it in the mass spec, right? So for example, if you separate CO2 with the GC, and then you put it in mass spec, you get the carbon isotopes, right? Or you can separate the nitrogen, put it in mass spec, you get the nitrogen. But it's much more complicated, right? Because you have the mass spec part, and that makes it really expensive, right? TCD is cheap, it's just a wire, okay? Plus some electrons. So this is the classic system. And then, what you could also do is you could have something like this, right? A mini multi-gas system, right? Again, these are boxes with sensors inside, and again, a number of electronics, data logging system, and so on. And essentially, you have these different sensors and infrared spectrometer. Those sensors, for example, cost $1,000. No, more expensive now. So close to $2,000, $2,500. Then you have these electrochemical sensors for SO2, H2S, maybe $500 each. And then if you have an electronics engineer, who can put together a box that connects the data and allows you to make those measurements, collect the data, put it on a USB stick, and then you can look at it. There's software out there. So we built these ourselves in our lab. We have built them for a long time, different sizes, small ones we put on a drone, for example. So you can do this yourself, or I think you can buy them now too. So that would be something that would be possible to do. For example, if you wanted to know the CO2 concentration in the air next to that beautiful hotel we stayed in, like Paradise Hotel, right? If you want to know if there's a high amount of CO2 because maybe the lake is degassing more, this instrument will tell you. The sensors are very, very sensitive. These sensors, these infrared sensors, they are good to like plus minus a couple of ppm. So very sensitive.
Does it quantify directly or just issue absorption each? How does the infrared aspect?
How does the infrared sensor work? So yeah, it's a little cell inside of this sensor. The sensor is small. The sensor is like a box about this. So inside you have a little cell that shines a laser and in the infrared spectrum into a little chamber. And the CO2 just goes into that chamber. And the absorption of the CO2 changes the output on the detector from the cell. Right. So infrared is really the only way you can detect CO2. There's no other good way to do that as precisely. So that's the expensive part of that system. And you have to kind of calibrate it. You have to zero it, right? So you have to have a little absorption, like a filter that filters out all the CO2 in the air. You put that into your sensor, that gives you the zero. Okay? And then you have a calibration curve, essentially. So it's again pretty straightforward. There's a lot of different literature on this.
The problems with humidity.
Not so much. You put a water filter in front of it and a dust filter, right? So these boxes, they operate on volcanoes for quite some time, like maybe 6 months or so. And then usually boxes are changed, new box with all the new sensors. The other one comes back to the lab, you check everything, clean everything, and so on. But this is very harsh environment. If you were to put that next to Lake Kivu, I think it could run for a long time. Again, it runs on battery or solar panels, kind of like a seismic station. CO2 flux measurements. Lake Kivu, there's obviously a bunch of faults. You could make such measurements. These flux chambers, again, there are expensive ones. This is a low-cost one, costs maybe now $8,000. Okay, so again, very, very easy to operate. Inside is the same sensor that we put in the multi-gas box, exactly the same sensor, okay, infrared sensor. And then for the data processing, you could use ArcGIS, which you might already have access to here. So once you start to do isotopes, things get a little bit more complicated, more expensive, right? So we see this little vial here, right? And here's a needle. So instead of connecting a gas sample bottle, we connect a little evacuated vial. This is the same vial that you use to go to the doctor and you take a blood sample. It's the same exact thing. So evacuated could be plastic. This one's plastic, this one's glass. And you collect the whole composition. You could analyze this on a gas chromatograph as well, right? No reason not to do that. Or you can put it into one of those machines, Picaro or delta ray machine, and you can get the carbon isotope composition. Now, this machine they don't make anymore. Thermo stopped making that, unfortunately. Now you have to go with the Picaro, or you buy a whole big isotope ratio mass spec. Okay. Picaro runs 100,000, not cheap. But this is my lab, and I can load all these samples in here, 150 vials, and then in theory we should just get data, but we still have to do some calibrations and so on. So if you do isotopes, things get a little bit more complicated, and for that it might be useful to collaborate with people who have it already set up. Here's a video. So very simple. Yeah, so if you were to do this, or if you collect this, you can make these kinds of maps. You can get the carbon isotopes. You can get a lot of information. And that's it. That's all I have. Thank you. Any questions?
Thank you very much.
Sure.
Yes.
There's a lot of material.
I think. So now we have a lot of work to do.
Yeah, now you have a lot of work to do. Yeah. If you want to do it, I think you can do it. If you don't want to do it, it's not going to happen. Are there any questions from online? Zoomland? No. Zoomland's probably asleep. Organizing, okay. Yeah. Okay. There's one. Thank you.
So, but thank you for coming. Yesterday about what we can do maybe more at the surface, but learn as much from what we can do at the surface in terms of gas.
I think we can do things in the lake too. We just still have to figure out
Yes.
what we can, how to do.
Okay, so until next time.
Next time. Next time I'll be coming here. There's gonna be a lab. We're gonna have everything running. Be great.
For the case of water bubbles that you get, it's possible to mimic the strategy that being by the columns that gas chromatograph.
Sorry?
The columns in the gas chromatograph
Yeah.
that I don't know if there is a reason or something that you can capture. You can just pump the water through it,
Yeah.
and then it absorbs the gas
Yes.
only.
Yes.
And then you can trap that
Yes.
within an aqueous environment.
Yes, exactly. Yes. I think you can have like a
Membrane.
you have a membrane. And there are such membranes that only allow gas
To be absorbed.
Exactly.
And water just flow along, or it's waterproof, but gas suction.
I know that people do this, for example, in the oceanic environment.
Yes.
In the oceans, they have membranes. They take the gas from the other side, and the water just passes. So on the other side, you would have to have a way to analyze that gas.
Yeah.
And maybe the easiest is to use a mass spectrometer, quadruples. You could get at least some compositions with that. You can't get a complete composition, but you could, or you could simply have a CO2 sensor Yeah, right.
CO2 sensor.
CO2 sensor. And you can somehow maybe figure out how much CO2 you would have per volume of water, something like that. Right? So if you put a volume of water and you have this membrane, you measure the CO2 for a certain amount of time.
Yeah.
And then you flush out the amount of water in that container. And then you measure again. Could develop systems. It's possible. I think it's possible to do. It would just require
A bit of
some
analytical
thinking.
skills and intuition.
Yeah, some thinking, sitting down and thinking about
Test.
testing.
Usually because in the lab, I mean, all these things you test in the lab, you say, I forgot this,
Forgot
which
this.
happened, and then
Yes, yeah, you don't want to drop in the bottom of the lake for testing.
Yeah.
So you'd have to do extensive testing, calibration. But I think for CO2 it would be quite easy with such infrared sensors. So maybe write a proposal to some agency to develop such a thing. The materials wouldn't be too expensive. Just time for people to calibrate. But I think we could learn a lot from that.
Thank you.
Yeah, sure. What is your name?
Edward.
You're Edward. Okay. Yeah. Nice to meet you.
Nice to meet you.
Yeah.
Okay, so I'll go, Tobias,